Okay, welcome to day 3 of week 2 of ST4 2020. We have in the morning our first speaker, Pratik Nandy. He's a PhD student at IISc Bangalore, and he's going to tell us about complexity, path integrals, and tensor network methods. Over to you, Pratik.
Okay, thank you for the introduction and thanks to the organizers for creating such events in this situation and give me the opportunity to speak. So I'll be telling this complexity methods, which is based on this path integral optimization and tensor network methods. It's a bit different than the previous things that previous complexity that you have come across. So I will start from the very basics to this tensor network things and go to path integral optimization. So definition of complexity. So today I will not go into the complexity things. I will mainly discuss this tensor network methods, and tomorrow I will go this complexity things. So this plan or reference or whatever you can see, this is the things. So the thing is that you don't have so many references actually, so it's very bit hard to read what this means actually. So but these are the main things. So I'll first discuss this mera things. This is known as multi-scale entangled denomination answers. Is a variational principle of preparing the ground state, is basically used by the condensed matter people actually. And then I will discuss the tensor enumeration group method, which is also used by condensed matter people to approximate the path integral in terms of the tensor networks. And there has some problems in this tensor TRG approach. But this is the very first approach when people applied this tensor network methods into this Euclidean path integrals or partition function things. And so this problem has been solved in this tensor TNR program. And so far, these TNR methods are complete and can be, can be realized accurately. And this path integral complexity that this gentleman Takane and other people have developed is basically this studied this TNR approach. So the connection is basically in this paper, this check paper. So I will discuss this tensor network things. And finally, if I have time, then I will I have time. Then I will discuss these recent papers. So this is basically this connection with the holographic CA theorem, which is in the context of this path integral complexity. So the first tensor networks. So the tensor is basically defined according to the numbers of legs attached to it. For example, this is a scalar which has no legs. This is a vector. This is just one leg I, and this is two leg. This is a matrix or a tensor of rank 2, and this is a tensor of rank 3. This is 3 open legs. So this legs, this is known as the free indices, and some indices can be contracted like this J indices J from this tensor. It is known as these bond indices. So these indices are chi-dimensional, means the indices can run up to 1 to chi values. So that is known as that's why is known as the chi-dimensional indices. The thing is that these indices may need not to be the same dimensional, but for convenience we will take the all indices are chi-dimensional.
Pratik, we have a question from Subbu. Subbu, do you want to unmute yourself?
Okay. How are the symmetries of these indices incorporated? Like suppose Aij is symmetric, how would I know?
No, there is no symmetry. So Aij, Aj, or all the indices that you will come across has the no symmetry and no antisymmetry property. So you can write anyway, in any pattern, Aj or something. So no,
Okay.
no symmetry. So in the coming slides, there is, we'll assume no symmetry. So you can write random. So these are the chi-dimensional. So for example, the tensor trace, this is another tensor trace. So if you write this tensor network language, the trace becomes a very simple thing. So these are all the tensors are contracted. So this is I, J, K, I, and from here you can see this is the AI two indices J, K, and C, K, I, and this two I as a contractor, so it becomes a number. This is a scalar because there are no free indices. So this is the next thing is the tensor reshaping. This means that
Pratik,
yes.
I think you're changing the slides a little too fast.
Okay.
Perhaps, yeah, just slow down a little bit.
Okay. So the next thing is that tensor reshaping, which means that suppose you have a given a 5-index tensor, so you can always write in terms of a 2-index tensor, that is the matrix. So for example, this three index you can reshape into IJK form, and 2 indices can reshape into ML form. So suppose all indices are chi-dimensional, so this means that all indices run up to chi values. So this is this 2 indices run to chi value and chi value. So together this runs as chi square value, and the 3 indices is a chi cube value. So it's a matrix of chi cube cross chi square dimension.
Shubham has a question here.
Yes.
So what? Sorry, can you explain this reshaping or regroup thing, business mode? Like, what exactly are you symmetrizing in groups or anti-symmetrizing in groups? Something like that. I don't understand what.
Okay. So reshaping means you just take this 3 index and group it one together. No need to do some in some symmetric and asymmetric way. Just three indices and these 2 indices. So this becomes a matrix, right? If you think these 3 indices are the 1 indices, this is a matrix, and these 3 indices are the 2 indices, 1 index. This is a matrix of rank chi cube cross chi square. So because all indices are runs up to chi value. So is that okay?
All right. Okay. Maybe maybe
I have a question.
One second. I mean, Akhil and Subbu, there is.
Oh yeah, sorry.
Akhil, do you?
Yes.
Okay. Any of you, Akhil or Subbu, please go ahead.
I think Subbu raised hand first, so Subbu should go ahead.
Okay, maybe he did first, but anyway. So how to see that in the left side it is not already grouped? Like I can't understand like what changed when you group.
exactly my question also. Like, I mean, what is the
Okay, so you can divide these indices up to from this value this way also, right? So this is a I and j, this is a m l k. From 3 indices you can have m l k also here if you divide this way. So this becomes a 2.
Yeah, what does that mean? What does that operation mean? You did nothing, right?
No, yes, nothing, just nothing. This is just a regrouping the indices, because this is in. But the thing is that this tensor networks actually very numerically. When you numerically do this thing, the thing is that the tensor network package actually do the matrix multiplication. So the tensor, whatever you do, you has to put it some in terms of some matrices. So
Okay.
so the tensor you have just put it some matrix. You can also group it some like I, and there is also 4 indices there. This is just regrouping things.
So okay, so just let me ask this. So this will help if you are trying to multiply another matrix to it, like
Yes.
in the okay.
Yes.
I see.
Yes. For example, you have a lot of tensors, and so all the indices are contracted. So every tensor you make a matrices like this, grouping indices anyway, whatever you want, and then you just multiply each and everything. So it's just a matrix multiplication of different order. So this is a chi cube plus chi square. If you group it some I and all the indices are 4 indices from here, so it becomes a chi cross chi to the power 4 matrices, something like that.
So if I have to multiply another matrix next, so that should have like two lines on the left and whatever lines on the right.
Yes. Yes.
Okay.
This way. So is that clear?
Yeah.
yes,
Pratik.
yes.
Pratik, so
Yes.
Right now these spokes aren't directed, right? These tensor legs. There's no notion of covariant legs or contravariant legs.
No, nothing.
So this partition into both two sides, I don't need to read it like that.
Yeah. So suppose you just go to some condensed matter classes. No, don't talk about any covariant, contravariant, nothing. Just from these indices.
Okay, Nishant, go ahead.
Yeah. So on the left side you have like 5th rank tensor. Suppose I, J, K, L, M. So if I take all of them value as 2, suppose 2 in 2. So, and on the right hand side, so the same element will be like 8 into 4, like 8 into 4 element of metric, like
Yes,
8 4
cross 4,
element.
8 cross 4 matrix. Yes.
Oh, okay. So
It's 8 cross matrix. So
okay,
whatever
all right.
matrix you can make a 2 cross 16 or 2 cross whatever. Just you don't need to find a matrix so that you can. This thing actually helps to when you do the calculation in computer, for example in Python or something somewhere. So you need to the package that tensor networks do actually produce this. I mean, in the package they do this tensor network into this matrix and then do the matrix multiplication.
Yeah, okay, all right.
Is that?
Pranjal has a question on the chat. He's asking that can we go back from the matrix to the tensor?
Yes, you can always just I mean free out these indices and can write these things. I mean, if you give us some chi cross, for example, chi cube cross chi square. So if all the bond dimensions are chi, so you can always write just a tensor like. Right? So currently, I am assuming that all the indices of bond indices are same chi dimensional, but that need not be the case. But for example, for now, I am assuming this.
Yeah, Pratik, I have a question of my own. So you said that the reason for this going to matrices from tensor is because it's probably more efficient while doing it in some programming language, right? So can you just comment on like what is the order of improvement of efficiency? Like if I suppose I have all of the indices takes values say chi. So if I keep it in the tensor contraction way or if I keep it in the matrix way, how does the computation efficiency improves?
No, the computation efficiency from here going from here to here doesn't need any cost. So the tensor language, the package sees these tensors as in this language. So the package, this computer doesn't recognize this tensor. They recognize these as these matrices. So that in the cost of language from this tensor to going the regrouping, this regrouping doesn't cause any cost. So the package itself, the tensor, the computer recognize this thing as a matrix. This thing as a matrix.
But that means that probably, I mean, you can write a different package which probably will be able to recognize tensors, and then you don't need to do this regrouping. Is that correct?
So far, whatever package has been developed. So the thing is that the matrix multiplication is very easy rather than this contraction, because in the Python there is a direct command do the matrix multiplication. So the whatever package you develop, you have to write in some language. So they are writing Python, Julia or MATLAB, some languages. So the thing is that whatever the matrix multiplication has a direct command, so you can do in the matrix multiplication. So this reduces the programming things actually. I mean,
so you're basically making use of existing linear algebra package.
Yes, existing linear algebra things. Yes.
Okay, I think Rohit has a question.
I have a comment on this, and maybe it's because they're trying to flatten the matrix. I mean, so it's like a vectorization operation. In that way, some calculations which involve matrices are much easier computationally. So it's like if there is an m cross m matrix. So sometimes what we do is we create another matrix which is a flat matrix. So it is of mn dimension of any side, like 1 cross mn or mn cross 1. We do that so that the entire thing is in a one long array, and in that way Python calculations are much more easier. I guess maybe it has something to do with that. I don't know. I'm just guessing here.
Maybe in the next language, for example, if you give a matrix, the computer do it in the vectorization process, as you have said. But for the tensor networks, the tensor things, you computer recognizes as a matrices. Then you can it's possible that the computer itself is using these vectorization things. But I am not aware of this vectorization things. So the thing is that whatever regrouping you are doing, you see these things as a matrices. That's the main thing. Is known as the reshaping. This is nothing. Both are actually same.
Okay, please go on. Sorry, Shubham has a question now.
So like, I mean, this grouping into 3-2, this could have also been 4-1,
Yes.
right? And it's on you to make the computer understand that it's 3-2 and not 4-1, is it? Or there is a way to, like, the computer decides on its own or something, like, yeah.
No. There is a. I mean, by hand I have to put these things
I see.
from the beginning. Yes. So I will give an link to the website that actually have a tutorial on how to do these contractions and everything. So you can just go and check. Just give a few lines.
Okay, thank you.
So this is just for the numerical purpose. But presently, whatever tensor network, so whatever you do, you just see the tensor as a matrices and do the matrix multiplication when you talk about these tensor contractions. So next, this contraction has some cost. For example, this reshaping doesn't has any cost, but the contraction, for example, if you see these things, this contraction, this has some cost. So the cost is basically given by this bond dimension, the indices shared between these two tensors. So for example, if you have a two tensor A and B, the cost is defined like this: mod A by mod B as A union intersection B. So mod A is just a total dimension of the tensor, where each tensor has a chi-dimensional indices has a tail, and A and B, this intersection has the total dimension of the shared indices. Let's give an example, then you can understand. So for example, this is the binary contraction. So this is a 3 cross 2 tensor, and this is a 2 and 1. So when you contraction means you make a single tensor which the three indices are 3 and this is 1. So these indices are contracted. The cost of the contraction is given by the formula that I have told. This A is basically, A has the 5 index, so is a chi to the power 5, and B has the 3 indices, chi to the chi cube, and the shared indices is just a 2 indices, it's a chi square. So all the cost is scales as chi to the power 6, this contraction. So is that okay?
What is the cost measuring?
Cost measuring, when you calculate the, I mean, in the tensor network things, when you make a tensor network out of the tensor and you do the, because you are actually building a network from a bigger tensor from a coarser tensor. So actually you do this is the contraction of between several tensors. So you see this, what is the cost actually doing these things. So I'll give another example. When you see this is the contraction actually needs a higher cost, and you are forbidden to do that. So let's take this example. This order of contraction matters. For example, if you have these tensor networks and after the contraction you are getting only two indices, like those two indices, this one and this one, all these indices are contracted. So if you do the first contraction A and take A and B, so the A has 3 indices, so this is chi cube. B has 2 indices, so chi square, and the share is shared 1 indices, so this is chi to the power 4. Now you take AB is one as a 1 tensor, and then C. So this AB total has a 3 indices, 1, 2, and 3, and C has 3 indices, 1, 2, and 3, and this share indices 2, this one and this one. This is chi to the power 4. So if you contract this way, first AB and C, you get a cost of two things, 2 chi to the power 4. But if you contract in the opposite way, first contract AC and then B, you get a chi to the power 5 plus chi to the power 4. So this is one order higher of this cost. So the thing is that when you do the this contraction in computer, you want to minimize this costing. So you prefer in this way the contract, not this way. So this means you first need to contract somehow this the inner tensors which doesn't have free indices, then the outer tensors we have a free indices. So this way you can reduce the cost. There are some inbuilt packages, some in Tensor, which actually chooses this cost rather than doing this way. So is all things are inbuilt in the Tensor network packages. So thing is that you understand these things, this contraction actually minimizes this cost, but the computer itself knows that how to do this cost to minimize this thing in the package itself. So is there any question?
Yeah, a very trivial question. So these paths, these links, so do they signify some process, or I mean, I'm a bit confused here.
These lines?
Yeah.
No, nothing. I mean, not any process in physical process. It's not that. But and later you will see that you want to put quantum state in front of this, but that will come later. Not
okay.
For now, this is just some indices and just some game. Okay.
Sorry, I thought the links were contraction between A and C. Right?
These are
these links.
Yes. This is some index. So you just want to contract this index.
Yeah. So Arnav, this is basically like, if you know, Roger Penrose had a way of visualizing this contravariant and covariant tensors.
Yeah.
So he said that contraction of two tensors is basically like if you take a link from one of the contravariant tensor and one of the link from the covariant tensor and you join them. So it's basically something similar to that.
Yes, this tensor network actually, the idea actually came from the Roger Penrose actually, but the condensed people developed in different language. So that now this Penrose things has not been used, but.
Sorry, I briefly saw some raised hand and then it disappeared.
Yes, Subbu raised his hand.
Yeah, me. I am fine now.
Oh, okay. I have a question, Pratik. So when you got this contracting the indices, Akhil also asked the same question probably sometime back in the chat. So how are you distinguishing between contravariant and covariant indices, or is there any distribution?
Right now there is no difference, right? Because I have just said, for example,
that's what that's.
For example, if I go back this way, whatever indices contraction, this is just a matrix IJ. I mean,
is there any way to like sort of, because if we have upper lower indices, then this grouping and the all will be non-trivial now.
I don't think so, because whatever we came across, this nothing matters actually. Whatever contravariant or covariant, you just do this tensors things.
Okay.
I mean, there's no matter. I mean, we'll see if this came across. I don't think that this will matter. So, for example, you can write the matrix as AIJ. Somewhere you can write this, right? But you can also write this A11, A12 or something. Doesn't matter. Okay, so this is whatever this contraction actually takes care of in this in the tensor network packages. So the package itself knows how to do these things actually to reduce the cost. So you don't need to bother about which way we need to do this contraction, but these things happen in this way.
So Pratik, there is a sort of well-known algorithm which will always minimize the cost given how complicated an algorithm.
Yes.
And it's inbuilt in the package.
Yes, algorithm is developed and this they're built in the package.
Okay.
Yes. So what is this tensor networks actually? So tensor networks is basically the DNS of the quantum state. Suppose DNS is the building block of the human. So the tensor actually make up some tensor networks, and these tensor networks are the basically building block of the quantum state. So you can approximate the quantum state in terms of this tensor network language that I will come across later. So currently, just think this tensor network as the DNS of this quantum state, fundamental building block. So thing is that why tensor networks? So this is a tricky question. So the thing is that if you have an n particle many body system, so you have a for example, many body system with some spins which can take plus and minus one, plus one and minus one. So the Hilbert's space is basically 2 to the power n dimensional, which is very large if the particle number is very high. So, but the thing is that the low energy eigenstates of the gapped Hamiltonian with local interactions over the area law of the entanglement entropy. The important thing is this local and this area law. This means these low energy states of gap Hamiltonian are not just any state in the Hilbert space. They are heavily constrained by locality and the entanglement area law. So whatever state we can, whatever the state we are interested are actually the low energy state of the local Hamiltonian, and they are they satisfy this area law. So we don't need to mess up with the all Hilbert space. We can look up some corner of the Hilbert space, which is which these low energy states are situating. So I think this is not clear. So maybe I ask, maybe somebody ask some questions. And
Pratik,
please go ahead.
are you going to explain more like how states, how tensor networks are building blocks for states? Because
yes,
like
yes.
Okay.
Yes. So so this is this statements clear? I mean, this low energy instance of this local interaction and area law.
So I didn't understand the low energy connection though. Why not?
Yes.
Why not? If it's local, I thought all of them should follow area laws.
Yeah, no. There's low energy states of a gapped Hamiltonian. So for the gapped Hamiltonian, these correlation things, the correlation functions actually follows the exponentially decay law. So they are, in the sense, they are local, and this area law, they satisfy the area law. For gapless Hamiltonian, the area law is mildly violated. Is not actually strictly follows this law. So I will consider only this these gapped Hamiltonian cases. But this whatever I will do also valid in the gapless case. Okay. So the low energies.
Nishant has a question.
Yes.
So area law, you basically mean the like if it's a lattice, so the area of the lattice or the subsystem, right?
I mean a subsystem, yes, area of the subsystem. So suppose you have a given lattice and you take a subsystem of this lattice. So the area law means that the entropy, if you calculate the entangled entropy between the subsystem and the rest of the lattice, the area entanglement entropy goes as the area of this subsystem region, not the volume things. This is true for the if the interaction is local, because in the if the interaction is not local, then the region inside this subregion will also contribute to the entropy. But if the interactions are local, only the boundary of this region will contribute to the entanglement entropy. That's the sense and locality actually needed for this area law thing.
Okay.
So any questions?
Subbu has a question. Yeah,
Pratik, so yes. In what sense does locality constrain states?
Locality constraint states.
You say they are heavily constrained by locality and entanglement area law.
Yes. Okay. So yes.
Area law I understand because that comes from the state. But
yes.
What about locality?
So locality means this Hamiltonian. You take this Hamiltonian as a nearest neighbor interactions. For example, for some Ising model Hamiltonian. So which are only nearest neighbor interactions. So in that state, you take this ground state. Is low energy states actually means this ground state actually. Ground state and few excited states.
Okay. Oh, you're just saying that if the Hamiltonian is local, then it will pick specific states to be its low energy eigenstates. Is that what you're saying?
Yes. Actually, yes.
Okay.
Yeah, Pratik, I think there is some discussion going on in the chat. Let me just point it out first, and then we'll go to Karan's question. Rohit is essentially asking that how do you measure area in a lattice? People are answering, but maybe you can also give an answer.
Yeah, so area actually in the lattice, in the tensor network languages, the area is calculated as a number of bonds that you draw some lines between the tensor networks, and this area. Maybe I will discuss it some later because I have to discuss it somewhere in some next slides. Okay,
so Karan has a question. Karan, go ahead.
Yeah.
Karan, you have to unmute yourself. Hi, Karan.
Is the
Are you
question
there?
asked? Or I don't think, yeah.
No, yeah.
Yeah, I'm sorry, I had a call. Yeah, I'm back. Hello.
Yes.
Yeah, go ahead.
Yeah, so I mean, so I'm imagining what you have is like a Hamiltonian with some nearest interactions, and by area law, you're saying that I can take some slice across this lattice, and the entanglement entropy is just dependent on those nearest neighbor interactions. Is this correct?
Yes. Yes. Because let me
Okay. And when you're saying,
show this
and
picture.
you're saying, yeah,
Yes.
and when you're saying, yeah, so basically across the boundary of A, there are some neighboring interactions connecting things on one side to the nearest,
Yes.
and that's it. That's all that you're concerning. And when you're saying low energy, you mean to say that it is only these interactions that you account for, not next to nearest or next to next to next to or whatever, those kinds of things. Is this correct?
Yes.
Okay.
So,
Yeah, thank you.
so this is some region inside your lattice system. So in the interior of this region, the spins doesn't contribute to the entanglement entropy because they are not because the interaction is local, so they are not connected to this from there. So only the boundary things, only the boundary the lattices which are in this boundary are connected to this contribute to this entanglement entropy because their interactions are local. So that's why the entropy follows the area law. So these states which follows the area laws and these states take a very tiny exponentially small corner of the gigantic Hilbert space. So this is a full Hilbert space. So this area law states is basically some fixed corner. So our aim to be is target to this corner rather than messing around the whole Hilbert space. So the tensor networks are supposed to capture these states. So whatever larger your Hilbert space is, you don't need to bother. You just fix your attention to this states which are satisfied with area law states, and the tensor networks are inbuilt structure which inbuilt structure for this area law which actually captures this this tiny corner. So the many body, so the big issue of the Hilbert space is so big, it actually doesn't matter actually for this tensor network description. So, and this method actually it has a close connection to the RG methods because RG methods is basically aim to identify the relevant degrees of freedom rather than the all degrees of freedom to describe the system. And the tensor network also doing the same things. It picks up some special corner of the Hilbert space rather than in full Hilbert space. So we can believe these two methods are closely maybe some way related. So that's why these RG methods are actually very powerful in doing this tensor network analysis that we'll see in next slides. So there are some examples of tensor network states. This is known as the matrix product state, which is a one-dimensional thing, and the two-dimensional version of this matrix product state is known as the PEP state. It's a basically two-dimensional tensor network. These all are used to simulate the ground state energy for a Hamiltonian. So these are powerful methods to introduce the DMRG approach, which is known as the density matrix innovation group things. So the numerical things. So all these things are basically used in numerical approach. Analytical approach, they are not very much powerful. I mean, not very useful. For numerical things, they are actually very useful. So these are some examples of tensor networks, which could be. So, okay. So until there's any question,
I had a naive question. Like, so when I draw these diagrams and like I check this area by what you said, like what are the adjacent bonds, something like that. Shouldn't I? Doesn't it look like each node is entangled to all the nodes around it? Say in this diagram you have on the screen.
for example, this diagram.
Yeah, so each node is entangled with each of the other nodes, is it? Because area law would say I have to count all the bonds because to check what is its entanglement. But then I would also have thought that there's some kind of some notion of degrees of freedom living on one side, and then you would say one side can get entangled only to one degree of freedom can get entangled at most only to another degree of freedom. this monogamy kind of statement. Maybe I'm wrong about how I understand both these
Okay,
statements.
so monogamy things is entangled monogamy things when you have the maximally entangled state, not the some few entanglement. Because when you have a maximally entangled state, then this monogamy things happen because you cannot entangle to the other state. Or if you have a maximum in maximally entangled to some state, but you have some entanglement, I don't think this is a problem.
Okay,
Suppose
when you show sorry, can I just say this? When I see this diagram, should I understand these bonds are the as some interactions between these points, or should I understand the bonds represent the entanglement between these points? What should I understand?
So bonds, these bonds are the precisely that we have taken this indices. So this is just you can think this is entanglement. I mean, these two tensors are connected or entangled in this way.
So this bond is not like a bond in the Ising lattice or something. It's
no.
Really
So okay, no. So no. Because these tensors are a representation of these Ising things. It's not the Ising model. Whenever you have two lattices sitting
so the
there.
bonds are not interactions, but it's really entangled. Is it?
Yes.
Am I right?
So suppose you want to take your entangled surface here. So the locality means that you have entanglement from this here, from these things, but not from this point, this thing, right?
But none of them are maximal.
Yes, none of them are
maximal because, like you said,
yes, none of them are maximal. The monogamy things happen when you have a maximal entanglement.
How would I represent a maximal entanglement in this picture? Say in the MPS picture where I have only one bond between each of them.
Maximal.
Maybe I'm just trying to get comfortable with these pictures. Yeah. So if I want to say, if I want to represent a state where two of the adjacent guys are maximally entangled, I should sever the bonds. Maybe like the first two guys are at entangled, maximally entangled, maybe in a bell kind of state. And then to represent that, should I totally rip off the bond between second and third dot in the picture A?
So if these things are maximally entangled with these things, this cannot be entangled in these things because all the entanglement that goes on this one.
So I will just simply rip off the bond. Is that
yes,
the right answer?
Yes, maybe. I'm not sure, but thing looks like this way.
Okay, thank you. Okay.
So any other question?
Pratik, I'm a bit lost here. So can you just quickly summarize that? Suppose I'm given these examples that you've shown, the MPS or PEPS. What is the physics question that we ask with this states, and then what is it that we exactly compute?
Okay, so you see there's a one free, free indices everywhere. So you are calculating, you can calculate the ground state, whatever you want to simulate. You think this ground state lives in these free indices. For example, this is a one-dimensional things, and this is a two-dimensional free indices. So your ground state actually lives in this free indices. So this is basically if you think this thing as a path integral that I will come later. So there is a one free open end. So where you prepare the state. So this is something like similar like whatever in the free index is a free open boundary condition where you want to prepare the state.
Okay, and then what do we do with this? What is it that we are trying to compute with this tensor networks?
These networks are basically an efficient representation of preparing a ground state that I will come across is a little more clear when I'll discuss the more tensor networks and actually show how this ground state has been prepared.
Okay, I think we have several questions. Karan first.
Unentangled, and then you build the entanglement at each step, essentially entangle the pairs.
Karan, your voice is breaking very badly.
Through some entanglement.
Sorry, I couldn't hear.
Maybe Pinaki, go ahead. We will come back to Karan after that.
Yeah, so I just wanted to ask that this is just approximation for the ground states, right? I mean,
Yes.
So you are in a gapped state such that it follows area law, and you are just saying that this is approximation for the ground states, right?
Ground state all low energy state but we'll take on the ground state.
But if it's not gapped state, then you cannot do this, right? I mean,
No,
you need some.
This is for the gapped state, gapped Hamiltonian state.
So okay, only for gapped states you can do this.
Yeah, but this is all this analysis also you can do for a gapless system also. But there's you need some adjustment of these things.
I see, but then there is no area law. I mean, that can be long range
Yeah,
entanglement or something.
in a gapless system, the area law is mildly violated because there is some logarithmic correction also. Right? So that some tensor network, there are some another tensor network that will capture this this logarithmic violation.
I see. Thanks.
Yeah, Karan, go ahead.
Yeah. So can you hear me now?
Yeah.
Yeah. So I thought this ground state is supposed to be unentangled, and then you build your entanglement over time by some kind of entangling operator, the AA dagger minus AA sort of guys over time. And those are always built on any two of these sites. So when you're saying this ground state, are you assuming that there is, I guess this is related to what was asked earlier, but like, are you assuming that there is entanglement here on this ground state? Or?
Yes, ground state is highly entangled. It's not a product state. So product state is some reference state. So in the many-body system, the ground state is highly entangled state. Right? It's not free of entanglement. So we need to build that entangled state. So we need to produce some entanglement in the ground state.
Okay, I see. So then let me reverse my question. So you have this entanglement in this state. You will eventually show how to build this entanglement from some initially unentangled state.
Yes.
Okay, so as long as that operation is known, how you build it up from any neighboring sites, I guess then this picture goes through. So ultimately you have some highly entangled state, and that entanglement is accounted for.
Yes. So you may remind that maybe you may think this is something like what Aranya said, is you have some product set and you want to build some other target state which is entangled state. So this is something similar thing happening also here. So this ground state actually is highly entangled state. It's not a product state, not a free.
Okay, thank you.
Can I ask something?
Yes.
Could you maybe denote by like in the usual notation using Ketsa and Brass, like how would you write the first state in A, maybe or B? I guess A is easier.
Sorry, can you speak louder?
Akhil, can you speak a bit louder?
Yeah, could you maybe write down for me the state which you represent by A, or maybe draw the tensor depiction of a Bell state or something like that.
Okay. So this is some slide. I don't know how to do these things, but this NPS state. Suppose if you have an n particle state. So if can I do this annotations?
Yeah, you can annotate yourself. Yes.
How to do this thing?
So on the top of your screen there is a bar.
Okay.
Pick the draw option, and then you can use your mouse pointer to draw.
Yes. So for example, so this is your, for example, you have some ground state and you want to build some.
Sorry, if you can type it text-wise also, I'll be fine. That would be easier if we can do that?
Text?
Yeah, or is there a way you can project the text on the screen? Maybe like a chat.
Is writing fine, right?
Yeah, I just thought it would be easier for me. Okay.
So this way you can represent a entangled state, right? So this is, you can see this is a ground state entanglement. So this thing, whatever this coefficients is actually 2 to the power n coefficient. And if I1 is takes 0 and 1 values and 2 values, this is a 2 to the power n coefficient. So you write this as MPS as something. As product, suppose you give some gamma 1, gamma 2, something like this. So you can write it as the product of gamma 1, gamma 2, and Okay, so one is some indices will be free. This I1 indices free indices. I1 free indices. I2. So suppose if A indices, B indices, gamma 1 has some A I1, gamma 2 has A B I1, I2. So this is why you can represent in terms of MPS. Is that make sense?
Give me a second. I'm trying to make sense. Thank you. I'm confused. Are gamma 1 and gamma 2 different kinds of coefficients? I mean,
Gamma 1 different tensor. So these are all the same tensor. I just represent this as gamma 1, gamma 2, calling this.
I said gamma 2 has 3 legs and gamma 1 has 2 legs.
No. These are some periodic boundary condition.
Oh, okay.
So because this is summed over this all the free indices, right?
Okay,
Some whatever. Because you have only one index is free. Has to one index is free. Because I1, I2, IN. So you have.
Okay, so I should add this. Okay. All the free dangling legs are like kets, and then the tensor itself represents the coefficient of these states. Is that?
Yes, these dangling legs are this. There's a free indices that this thing I1, I2, I3, and all these indices that between this B, C, whatever, that has to be contracted everywhere. The tensor. Yes.
Thank you.
Okay. So that is just how to read it. It is this thing.
Okay, I will do that. You go on.
Because
Yeah, go on, Pratik.
I cannot go to the next slide. Something happened.
I'll just click.
Okay. So next we will do see how the RG things actually taken into account this in tensor network things. So we'll discuss this entangled renovation things. So before that, we'll start what is the motivation for doing this. So consider a one-dimensional lattice, some quantum system of Hamiltonian only nearest time interaction that we have previously discussed. And our goal is to compute low energy properties of the system, which is assumed to be in the ground state. For example, some physical operators in the ground state that we'll discuss these things. So currently we don't know what is this ground state actually is. So we have to prepare this ground state in some way. For example, so we can compute these things, this correlation functions. So this exact diagonalization, suppose you have given a small size Hamiltonian, you can diagonalize it and find the ground state of the Hamiltonian. But if the lattice is moderate to larger size, then you cannot do this exact diagonalization things. So you need to do some better plan. For example, some numerical things, some Monte Carlo things or some things. So tensor networks actually has a different advantage over this Monte Carlo things. So suppose we are doing only this tensor network things. So for the larger lattice, we need a better plan. So you'll see this how these tensor networks are useful. So the tensor network uses this RG technique. So this historically has been developed by Kadanoff, the block spin transformation that everyone is familiar, and this Wilson, and this DMRG thing that Steve White has been developed. And this DMRG actually uses this fact all the networks has been represented in MPS states. So still now DMRG is the most fundamentally used and most widely used tensor networks algorithm so far in numerical things. So later developed tensor network things is tensor innovation group, and then Vidal talks about this entangled renumeration things, and then comes the TNR thing. So all the motivation behind this is to transform from some lattice, which is some Hamiltonian, to a coarse-grained lattice, which has a different Lagrange lattice. This is lattice and this Hamiltonian H prime, such that this correlation function is become unchanged. So for this prime states are basically the ground state of H prime. So we'll see how these things happens. So this renumeration technique can be used to address for the larger lattice size. So first we'll discuss the tree renumeration things. So as said previously, consider this one-dimensional lattice thing. Is some question?
Or only please go ahead.
Yeah.
Hi.
Yeah.
Yeah. So can you go back to your previous slide? Actually, the next one.
Yes.
Yeah. So in this one, when you mention this transform lattice to a coarse-grained one, and the expression you write is similar to what Adwait was talking earlier in the first day, where he was taking sort of two rows, one is row and another is row bar, and taking expectation values of operators. But you have here you have taken expectation values of, say, arbitrary number of k operators, and you equate the two sides, right, for psi prime and psi.
Yes, yes.
So are they related in some way, or because they are both coarse grained thing in here? Do you have a comment?
So the question is very tricky because I have not attended the first talk. So I don't know what he has talked about. So
okay.
So maybe we can discuss it later.
Yeah.
Question, Pratik, I missed why are we going to this RG techniques again? Could you briefly say that again?
So just slides.
Yeah.
Okay. So RG techniques is basically you want to go from a larger lattice size to a coarser lattice size so that your expectation value remains unchanged. So in this way, you can target a very large lattice size. Suppose you have some 128 cross 128 lattice. So you just do some coarse graining techniques. So go from a say 32 cross 32 and then 16 cross 16 lattice. So then you can take this 16 cross 16 lattice and maybe an 8 cross 6 lattice. You can do the exact diagonalization things, whatever. So your main goal is to reduce from the larger lattice size to lower lattice size in RG technique, so that this whatever observables, this correlation function doesn't change.
Sorry, I was understanding we are doing this tensor network business to primarily keep track of the entanglement.
Yes.
But then doing RG would also drastically change the entanglement because I'm essentially cutting down.
Yes. Actually, yes. I'm going to discuss that because you have to do you have to do this RG techniques in a clever way so that this entanglement structure has to do some entanglement structure. You cannot do the arbitrarily. So there is some way actually.
Okay.
So this tree derivation thing. Suppose you have some block in your lattice, which are taken as many lattice points, and each lattice points in the block has a vector space Vs. So the total Hilbert space of in the block is just a product of this all Hilbert in each lattice site. So after coarse graining, this block is averaged out to a single point, single point in some coarse grain lattice, which has a Hilbert space of Vs prime. So we define this map as an isometric map, which defines a V. This is V block to some single state. So maybe okay. So it will be clear later. So actually, I'll say. So this is a larger block in your lattice, and you want to make a coarse grain lattice from this similar spirit like a Kazanov block split transformation. So this is a map, and this is dual map is just a reverse map when you go from one single state to a block state, a block size. So this is not actually the inverse of the lattice because you cannot do the inverse because some information has been lost in this way if you do the coarse grain things. And this is not a unitary operator, has to be because this is some information has been lost also. So this thing satisfies this omega dagger omega equals to identity, and omega dagger is not identity because you cannot do the reverse process. So that's why this is named as isometry, not the unitary operator. So suppose this picture will clear. Suppose you start from this state. So omega dagger, omega means that you first do a omega. So this is your some block. So you just do the majority rule. So to identify what the coarse grain thing is. So everything is plus. So it is plus. So when you do the omega, this W transformation, this all becomes is up. So this may not be the same as these things. So omega is W is not actually the inverse of this W dagger, as I have previously talked. So suppose you start from a point from this lattice, and you do this W, so you get this this lattice, and you do this W dagger. So you go back to this slide. So this is an identity operator, right? You go from this way and this way. So this is a identity in this space S prime. This is only a single. But if you understand this, first do this W dagger and then W. So W dagger actually do what it does. Suppose you start from this thing, this W dagger makes a single lattice, and the W is actually make some other lattice, not this. So it's not the identity operator. That
Pratik,
yes.
Rohit is requesting, can you please summarize this last slide?
This slide?
No, the one before this.
So this slide is that the summary is in this slide. Okay. So this is a map. That is a W map, W dagger map, which is you map from a block to a single spin. And this W is a dual map. It's not the inverse. It's a dual map. When you map from a single side to a block, and this W dagger W is an identity in the spin, but W dagger is not the identity. Is a projector. So that's why it is defined as an isometry. So in this map, this is clear because this relation. Actually, this relation using this picture.
Okay, I guess you can proceed.
Is that clear?
Sorry, by the identity of spin, do you mean that they get you to the same number of spins when you operate
in the same structure, just same structure. Not only the same number of spin, but the same structure. For example, this thing, W dagger W. If you start from this thing, okay. So first you apply this W. This has been implanted from left to right. Sorry, right to left. So first you apply W. So this becomes all spins, and you W dagger is just force grain version of this thing. So these become exactly this thing. This is your identity in the single spin. But if you act as a W dagger, so W dagger means you are force graining something. So you start from this here, is W dagger, you get this thing. But you again, if you reverse it, now if you do the W things, so this becomes this thing. All are supposed to. So you may not be back from this thing. Suppose you start from this thing. This thing also goes back and then comes back this thing. If you start from these things, then is W dagger is identity. It is okay. But if you start from this thing, is W dagger take you from this side, and then W is making you this thing.
Sorry, I don't understand the identity in the spin business. Like, so suppose you start from the block in the second row, like that, with 3 spins up and 1 spin down.
Yes.
So what is the S prime for that block? Is it 3 or 3?
No, this one. Yes, S prime is when you do the coarse graining. So S prime is this one. S prime, either up or down. And the block means the full block, the full space of this block, this VB, this block. So spin, the single spin is just a spin. This is up.
So in what sense is this an identity? Sorry, so you take a block, you apply W and W dagger simultaneously, and then what does the identity mean then?
Identity means this operation actually gives you back to this back the same state. So as if you are not doing anything, right? So what that identity means?
But it is giving me something different, right? Maybe I'm not. Yeah,
no,
this is.
Suppose you start from this thing.
Yes.
And you apply W.
Yes.
No,
W dagger.
No, W dagger. Yes.
Yeah.
For example, this thing W dagger.
Yeah.
You apply this W dagger, you get this thing.
Yeah.
Okay.
Yeah.
Now you apply W. So for
Yes.
example, W means you will get this state, not this state.
Correct. Correct.
So this is not the identity. It's not the identity things that I mean. You're not reverse back into this state, but you're getting some other different state.
Yeah, but there is one I did where you like yeah.
If you start from this state, you back W dagger, then you can apply W, you get back that state, of course. But there is I mean, this
No,
is not,
I completely understand your second inequality, that W dagger is not an identity on the block space.
yes.
But what is this spin space identity that you are getting? Like
in suppose you start from this thing. This is supposed you have to start from this thing because you are acting first W, not so. This is not from here because you are acting first W. First W you are acting, so you get this state. Now you W dagger, so you force getting these things and get back these things.
Oh,
so okay, so this is just the same thing they are getting.
Oh, okay. I am not supposed to think of as acting W dagger W on the left hand side.
No, because you cannot apply W because W is acting on a single spin, right?
I see. Okay. Sorry, sir. Yeah.
So this is things. These things when W dagger is just a projector, is not an identity. So that's why this is known as isometry. So the nomenclature isometry means that if some operation satisfies these things, one is identity, but the other way is not an identity but a projector. These things called a project. Otherwise, this is called unitary.
Okay, we have several questions. Subbu, go ahead.
Yeah, so I'm just curious, like, what is your rule for W dagger in that diagram? Because, like, suppose I had like 2 down and 2 up, like, what would you have taken? RHS
that's a tricky question. That's why I have omitted this thing. I have not shown this thing because Kadanoff block spin conservation actually takes the majority rule. So majority rules, for example, if you have 3 things, so you take the up spin. If you have a 2 spin, 2 up, 2 down, you do a random things. You can take both spin as up, both spin as down. You have to do some random choice. That is
okay.
That's why I have omitted because this is tricky.
Okay, Devanshu.
Hi. So my question was very similar to what Subbu just asked. Can you explain exactly what is the action of W on this spin? I mean, I'm not getting this because I'm concerned about the uniqueness actually. What guarantees that you have got all 4 spin up? And instead of, I mean, I was assuming that you would get 3 up spin and 1 down, right?
Okay. So suppose, hello. Yes. Yeah. So suppose you make a block of 9 spin. Okay. Instead of 4, you make a block of 9 spin. So W means if you get an up spin, in the code spin version, if you act a W, you all get an up 9 spin as an up spin. Whatever spin you get is an up spin. So all the 9 blocks spin is up spin. So W means this map. So if you have some spin, you make all spin as an up spin. Some operations. And W dagger is just take the majority rule and make this a single spin. Is that clear?
So, I mean, my question is, if I want to have say going back to your example, I want to get a block of 9 with all down spin. Okay, yeah. In this slide, is there a well-defined like closed form expression? What is the action of W on a generic state?
No. This is actually called this isometry. So in some wavelet basis, they have some closed form expression in terms of Pauli matrices, but they are not well defined. I mean, not a closed form expression. No. This is some understanding of some operations. In the later slides, I will also talk about many times this W and WR, but I will not show any closed form of this expression. So this is not known actually. Instead of one example, analytic example in the wavelet basis, which is just some closed form expression.
I was looking for. Okay.
No, there is currently no expression.
Thank
so I will talk about this WW many times, but I will not show any closed form of the examples. I mean, expression for W and W1 because it is not known. So it's some operation that do it. So any question?
Thank you.
So this is the isometric things. So this is for the small W is for the small block. Now you make the lattice into a many different blocks, and you do the things that the tensor product of these operations. So for this we need that all blocks are identical, so that same W can be executed. This reflects the translation invariance of the lattice system. That will from the beginning we will take this assumption, this lattice is translation invariant, so that you can make all W's lattice break into similar blocks, and you do the transformation in the whole blocks. And for this capital W, which is act on the whole lattice, it's also satisfies this isometric property.
Pinaki has a question. Pinaki, go ahead.
Yeah, so these W's, these are just block spinning, right? This cross scaling.
Yes, cross scaling. Yes.
So if you have this Hilbert space and you just sort of project it to some low dimensional space, so that can have some analytic expression, right? I mean, just some metric operations such that you go from larger, say, bigger vector space to lower dimensional Hilbert space. We can define a rule, right?
Well, in this tensor network language,
no, I'm just saying that suppose you have some Ising model, say transverse Ising model. Then you have two spins. So you consider all four possibilities. You drop the high energy states. You just project it to lower dimension. So low energy Hilbert space. So that will sort of rest. So this will implement the way you do the. I mean, at the end of the day, you are interested in the ground state, right? So you just drop high energy state. So I'm saying that there can be a systematic way of sort of writing down a projector such that it's just like standard, real space RG. So there can be some expression for this, right?
I have not seen actually in all the papers just talk about this W, but because these things actually they implement this W in a numerical way, so they don't talk about it in analytical. So
true. I agree that. Yeah. Particularly this kind of tensor networks, they are mostly interested in numerics, but I think there will be papers.
Yes.
Quantum RG. Okay, maybe you can.
I'm not familiar. Maybe you can send some in the Slack also. I'll do that.
Sure. Yeah.
But one thing that I said that there is a closed analytical expression in terms of Pauli matrices in the wavelet basis there. This. So there's only one example known. I know actually.
Yeah. Okay. Thanks.
So this capital W is for the whole lattice space, and this you can understand this picture. So you take these three spins and you force grain the version. So you get a force grain lattice. So this what is your W doing? This is not actually W. This is W dagger. What W dagger doing? If you interested from these directions, this is what W dagger doing. From 3 spins, you are taking this 1 spin. So this is your initial lattice, and this is your Porcel lattice. So okay, so in this way you can generate a for getting a RG flow. Suppose you start from your initial lattice and go some Porcel lattice doing some multiple different consecutive operations of W dagger actually, because this is W dagger what takes from Porcel from a bigger lattice to Porcel lattice. So there is T is somewhere you just force gaining flow ends. So end means you do it by your hand, whatever if you want to do it, stop there by your hand. So for the infinite lattice system, this flow reaches a static state when subsequent applies of W do not change the system further. For the final lattice, this is naturally reached when the whole system has shrunk to a number of sites smaller than a force gaining region. Suppose you force gain from 3 sites, and you after force gaining you reach the final lattice system, you reach two sites. So then you stop, because then you can't apply this force gaining because this W takes only 3 steps to one step, one lattice. Okay. So when you reach that state, you do a you do another map which is known as this top tensor. This is just a penultimate tensor to this penultimate lattice, the final lattice is just a single lattice. So coarse-grained the whole remaining lattice, whatever the lattice is, just to a single step. And we can also stop, as you said, in a certain depth, and for that case we need to apply several top tensors to reach a single coarser lattice for this single point of view. So the point is that you do stop by hand whatever up to remuneration you want to stop, and then you apply this top tensor and you reach just a single point.
Orgo has a question. Orgo?
Yeah. Pratik, can you just go back to the last slide? Probably very dumb question to ask, but no, the after point one. Yeah. So when you are doing these W dagger operations, so as you have showed earlier, let's say you have initially you have 4 blocks and your W dagger is converting it to one single spin, right? The way you have showed before. So
sorry, can you repeat?
Yeah, I was just asking that as you have shown before that your W dagger, let's say your initial blocks are with 4 spins and it's projecting out like you are getting to 1 spin, right? So input is 4 spin, output is 1 spin. So now if as you have chosen your W dagger the way you define, I thought that you can choose your W dagger to be anything. Like for example, let's say whatever be the spin structure, you will always project out up spin. Then what's the point of even doing all this W0 dagger, W1 dagger and all? Like at the end of the day, whatever spin you will get, all of them are up spin. Like what's the, what are you gaining by doing this W dagger operations?
Oh, okay. So no. So actually, okay. So this is a very schematic diagram of what W actually means. So this is in the, when you apply this in your lattice structure, you this W is a different. I mean this. This. If you say this is the upspin, this is the downspin, and the W is the upspin. The W may not be a upspin. It may project into a downspin also. But
what is the expression for that? How do I know it? I mean, as Devanshu was also asking, like, how do I know it? Let's say this 3, for example, if that is non-trivial, let's go back to 3. Let's say I have given you one of them is up, down, up, and second is up, up, up. Okay. Then how do you differentiate between these two? Is there any difference?
Okay, so
I mean, that, I was thinking that probably this W daggers are some kind of quantum gates or something. I mean, I don't know. I was just thinking that probably they are something like that. What Odonno was talking. So, is there something?
Suppose this is some lattice point which takes a value plus 1 minus 1, right? Or example 0 or 1 state, right?
Right.
This
Okay.
All 3. Okay. So if you this three spin you project into a 1 spin, which has a structure 0 and 1 again. Right.
Either 0 or 1, yes.
Yes. So all the spin have a 0 and 1. So here also you have a spin of 0 and 1. So if you coarse grain, this also have a spin 0 and 1. So you do not. I mean, you are not taking the 0 and 1 spin and projecting to just a 1 spin. This is it becomes a classical things. So it just becomes a 0 and 1, and this doesn't change the Hilbert structure. It's just projecting 3 spins to a 1 spins.
I don't understand. Doesn't change the Hilbert structure meaning?
I mean, this is just a 0 and 1 spin, for example.
Right. Right.
Okay. This is also 0 and 1. This is also
0 and 1, 0 1.
All are 0 and 1.
Right. Right.
Now you take 3 spins and project into 1 spin.
Right.
So this has also structure 0 and 1.
Agreed. Yes.
Okay. And you again do another things. For example, these things, this tree, and again.
Yeah. But what I'm asking is that from initially 0 1 0, or you can think of this if you're considering 0 and 1, so there can be 0 to 7 numbers, right? So you are basically choosing input as some 0 1 0, and then you are having some output. What I'm asking is how do how are you doing that, or you will go give us some expression, or is it?
No, as I've said, there's no example, so I'll not give you an example. But
okay.
if you have to distinguish from this picture to this picture, this picture you are taking 4 lattice to a single lattice. This may be some down also. There's no need that maybe an up. Okay, maybe some down. If there is all the down spin, I mean the majority rule. Okay, so this is a schematic diagram what W and W are actually doing. Is not the same in the same way you can think, because this thing is just you take 3 spins and just project into 1 spin. So I said that the Hilbert structure has not changed. That means these states are 0 and 1. These states also the 0 and 1. So this is a two-dimensional Hilbert space. If each spin is also two-dimensional Hilbert space, 0 and 1.
Right.
So there is, I mean, you're not projecting all states are 1. I mean, it's not W is not doing that. You are taking whatever 0 and 1 you get, you project into a 1. In that way, it doesn't make sense, right? So the W is something that this 3, 4 things makes just one thing, and the structure doesn't change. So you have to distinguish from this above picture in mentally that in this way.
Okay.
Is that right?
I mean, partially. I'm just stuck that, let's say I have to do some real calculation. Then how do I do it? That was the question. Because you are operating simultaneous, right? I mean, not simultaneous, successively W0, then W1, then W2. What I'm saying is that you don't need W0, W1, W2. Just consider n number of blocks as one input and then just output it. What's the need of W0, W1? You can just do one W dagger T, let's say. Only one W should be enough. Then in that case, I'm just confused, like how to.
Although you can think of the actions of these Ws as doing the RG flow. I mean, you can always say that. So suppose you have 5 Maskels in your theory. You can always say I can go from the 5th highest Maskel to the 4th highest Maskel by one RG step, and then to the 3rd, then to the 2nd. Or of course, you can always say that I will come down to the lowest Maskel by integrating out every massive state in one go. That's what you are saying. So, I mean, you can always take RG flows at one step at a time, or you can always, combine those steps in one big step if you want.
In RG flow, it's fine. I'm just asking that one.
These actions of Ws are also like RG flow, right? I mean, this is how you do in StatMake, that you first define how you, given a lattice, how you define it into different blocks. You prefix the size of the blocks. And then on each block, you give a consistent prescription, as I think many people are also pointing out in chat.
That is what it is.
So the consistent prescription, for example, if you give something like this, that I don't care about what is the average spin in the block, I will just always replace it with up. That is not a good prescription, right? As Subbu is pointing out that you will lose too much information.
Right.
The correlation function from that coarse trend thing is meaningless. But suppose you give the original Kadanoff prescription that whatever is the average spin in that block, you will replace the entire block by that spin. And if your average spin is 0, then you just randomly replace it by either up or down, because you don't have a 0 spin in your system. So that seems like a reasonable thing to do. And of course, I mean, if you can take a continuum limit, then there is a sort of more systematic way of doing it. But in the statistical mechanics, I think this is the way you do it. So I think there are several comments, Karan, Subbu.
Okay.
So can I just make like one comment? Like, it's just that like even he had written this equation where like the coarse-grained observable should still have the same correlation functions. So if that has to happen, then you should have some sensible W dagger.
Okay, that makes sense. Yes. Okay. Yeah. That is what I was actually.
Right.
Okay. Good. Thank you, sir.
Thanks. Yes. Thanks.
That makes sense.
Karan has some comments to make, I guess.
Yeah, it's just that I mean, I don't see how to construct the sensible W dagger, because if you have 4 spins, for example, as you showed in your diagram, or you can go to the other one where you have L going 12 prime. Yeah, this one. And I take the 3 spins, right? The 3 spins have some entanglement between them. They have some correlation. They have something. And I project this onto 1. So how could I possibly preserve that structure and going from the 3 to the 1?
This 3 to 1, they can have entanglement. They can have entanglement too. Maybe these 3 boundary spins also can share entanglement, right? So
yes, but how does the final one capture that? Is my question.
Yeah. That is the precise way we will talk about entanglement renovation things. So we will see the process of tree renovation thing is not the good way. What I'm explaining. This is not the good way to do things. You have to do it in some better way. Yes, you need to take this entanglement structure into the consideration. That is the next part of this entanglement part. Yes.
Okay, thanks.
Okay. So if you apply this successive transformation, so this becomes a network structure. This is known as the tree renovation network. So at each level, you just group into 3 things, random, 3 spin, and do this coarse-graining things, and you get each successive layer some coarse lattice size. So the problem as was Karan was asking, the short range entanglement gets accumulated in each port scanning block in each steps. Suppose you have an entanglement in these two spins. After coarse graining side, this you reach a one spin that doesn't have this entanglement, doesn't know about this entanglement thing in the sports lattice. But if you take these two spins, after you don't know which states are entangled, which states are not. So suppose you are coarse graining in this way, and these two states are entangled. Then at each level, you are in entanglement increasing, right? So when you go to the coastal lattice, your entanglement gets accumulated. So this is not the thing that you want, because in the very specialty of RG thing is remove this short range entanglement. You see this is a very much problematic of this tree things, and this actually fails. So this is not the proper way to do things, do the coarse graining thing. So is that answer your question?
Well, yeah, you're saying it doesn't work. So yeah, okay.
It doesn't work. Yeah, I've told, but ultimately what I told, it doesn't work. Yes.
Yeah, so you're breaking entanglement, just to be clear,
yes,
right?
Yes.
Actually, this sentence is not clear to me. Like, what are you saying? Short range entanglement gets accumulated where?
So when you do the coarse graining things, right? So the things is that whenever you want to do the coarse graining things, you want to remove this short range entanglement, because your coastal lattice doesn't know the information about this entanglement structure, right?
Okay.
So suppose you have this entanglement in these two lattice points. So if you do the coarse graining things from this lattice L2 or whatever L1 per se, it doesn't know about this, whether they have an entanglement or not, because this is just but if the entanglement in this way and you do the coarse graining things in this way, suppose you just do things, so your entanglement makes appears in this stage, right? So further you do the coarse graining, your entanglement gets accumulated in every steps. So it's not removed.
So you want to remove entanglement and it is not removed. Is that the problem?
Yes, because the coarse graining actually wants to remove this entanglement. Right? The procedure, very procedure of coarse graining entanglement in the RG things is to remove the entanglements from this low.
Okay.
Very
Okay, thanks.
So yes. Somebody has some question.
Karan, can you go ahead?
Yeah, I just wanted to know how this is explicit. I got your point that there's like you've restricted to nearest neighbor interaction. So at every step, I can see like each of those blue things which you've drawn is the entanglement. But how is this manifested in this W prime thing? Because if I started with L0, then I had, let's say L0 had n of those dots. Then I have n by 2 entangled pairs by your construction to begin with. And and n by 3 on the top, right? I mean, there is some entanglement breaking that is manifestly happening, but then at every step, you're manifestly putting it by hand. You're again saying that after I've done this projection, it should be that the nearest neighbors are entangled. So this looks like you're putting in an assumption by hand following the projection, or is this part of the projection itself?
Yes, this is because this is a very problem. I mean, this is a inbuilt problem with these projection operators, right? Because they doesn't know which states are entangled and they are projecting randomly, right? So they are creating entanglement in every steps.
No, I'm asking, how do you see that it's creating entanglement? Since it's random and it's just projecting out one, how do you see that the step at L1 is exactly as you've shown? Is this like something you can't rule out, or it's something that you are saying?
Something that I can't rule out, because these ground states are highly entangled, right? All states are highly entangled. So if you do a random coarse graining things, so there is high chance that in the next step there's also remain entangled. So because you don't know after this, so
yeah, thank you.
So this is a possibility. Maybe it may possible that these three things only these three are entangled. So in the very next step, you just entanglement is lost. This is very possible, but this is very highly unlikely, right? So that's the case. So the general rule is that this procedure doesn't work because it creates the accumulated short range entanglement into the coarser lattice. So this is the problem. So as I said, this doesn't remove the short range entanglement. It sharp contrast to ideas of Wilsonian urging. So and this actually depends on the choice of block size, like which blocks you are choosing, what the location is, and what is the shape. If you consider the higher dimensional version of this thing, and this is a very non-physical artifact of the scale. So we have to come up with a clever way. So to coarse graining these things and solve this problem, so that in the next step, whatever you do, this entanglement structure doesn't remain. So this is known as the entanglement remuneration. So entanglement remuneration is built to precisely solve this problem that we run into this scheme, and it aims to remove the short range entanglement between blocks before applying this coarse graining. So the coarse graining actually takes up this entanglement. So we have to come up with some procedure which removes the entanglement before the coarse graining, and that is that has been done using this disentanglers thing. So disentangler is just a unit transformation that operates on sides at the borders of the blocks, because we want to remove the entanglement from the borders to reduce the local entanglement between them. So this, for some mathematical language, is also some interior operator which takes two spins and project some different in the coarser lattice with some same number of dimensions. So this is a unitary operator. It's not projected things, and these new sides are then fed to the coarse graining procedure after you do this coarse graining things. For the full lattice, you define this as a total U and U dagger for translation invariant system. So as soon as you draw the picture, this will clear. So this is just the disentanglers. So the disentanglers means that these disentanglers between the entanglement. So these two are entangled. So there is some unitary operation that will remove this entanglement structure. And now if you do the coarse graining things, there is sort of short range the entanglement doesn't accumulate into the coarser lattice. So we have a expression for how this expression, how this disentangler acts. I'll show how this disentangler acts into some lattice space. So the main point is that before the coarse graining, you need to apply these disentanglers to remove the short range entanglement. So that the entangle doesn't carry over the coarse lattice. So is that clear?
Sorry, Pratik, now you have a coarse graining procedure which is invertible. Is that what you're saying?
So yes, now you first apply these disentanglers things, so that it removes the entanglement from the boundary things, so that whenever you do the coarse graining things, your entanglement doesn't accumulate.
So does this break the translation invariance?
No, because it doesn't break the translation invariance, because for an infinite lattice size, this actually keeps the translation in, because you are assuming these things are this, but it's actually not. It doesn't break the translation invariance.
Okay.
Because if you apply the same disentanglers everywhere, in every step.
When you show the example, it will be clear.
Yes. That's a precisely made construction.
Okay.
Pratik, I would like to point out that you have a couple of minutes left. So try to reach a suitable.
Maybe I'll give the example and then stop. So there is an example. What is this disentangler actually is? Suppose you have a situation of 4 spin, and this R1, S1, R2, S2. Okay. So and these R1, S1 are highly entangled, maximally entangled. So these are in some Bell state. So the whole state of the system is just this system. So these states are highly entangled, the first and second one. Now now you want to do the coarse graining before applying this disentanglers. So what you do is you take the reduced density matrix of this with respect to this R1 R2, and you get the highly maximally mixed state, because due to this you get this maximally mixed state because this R1 S1 and R2 S2 are highly entangled and by your construction. So you get a maximally mixed state. So now you want to see how disentangler acts and remove this entanglement. So what you do, you take an unitary operation. As I've said, this disentangler is the unitary operation. You can check this unitary operator. So you take this this unitary operator with some this coefficients, and we apply this state before this the entangled state, right? So what you get is a zero state. So now if you get the reduced density matrix, this is not XML mixed state, is neither mixed state, is a pure state. So what disassembly actually does is actually does this acts as a unitary operation that changes the basis. So this basis, from this basis you are changing the basis. So unitary operation doesn't preserve all the structure. So you change the basis and you do the coarse graining. So the operation of disentanglers actually can be realized in terms of the basis change. Is that clear? Any question?
Can I ask?
Subbu had his hands
okay,
raised.
go on.
Yeah, so I have two questions. So one thing is like in your earlier picture, were you assuming that only the nearest neighbor ones were entangled?
Yes. No. Okay. Maybe they can entangle in this way also. Maybe suppose these are also entangled, right? These are also entangled. Yeah. So if these trees are entangled, we don't care, because after all, after them next step they do not create the problem. The problem is
that's not what I'm asking. I'm asking like between the two blocks itself. Okay. If let's say first one of the one block and the third one of the second block, can they also be entangled? Because it seems like in your next picture, when you take the disentanglers, you're only applying them to the nearest neighbor ones from two different blocks.
Yes, because this nearest neighbor also only creates a.
That can only be entangled, is it?
Yes, because the nearest neighbor can be also entangled. These points and this one are not entangled because we are taking only the nearest neighbor interactions.
Okay. So let me go to my next question, which is regarding this example. So this taking the partial trace to go to the reduced density matrix, was that your definition of coarse graining?
Yes, that's the definition. Okay. If you ask this what W is, actually this is a kind of coarse graining. Yes.
But then, like you said earlier, that if you have entanglement, then it leads to accumulation of entanglement. Whereas here it is just leading to a maximally mixed state. So I don't see like how you are speaking of this as entanglement.
So entanglement because if you want to remove this entanglement between R1 and S1, you want to coarse grain, right? This S1 and S2, but this is highly entangled. R1 S1 and R2 S2 highly entangled. So if you coarse grain, the state that you get is a mixed state, is not a pure state. So that means there has some entanglement between them. So you don't want to be this row S1 S2 as an
that is not true actually. For S1 and S2, what you have is a mixed separable state. So I don't think it's an entangled state, but probably you don't need a mixed state. You want a pure state at each step. Is that what you're saying?
Yes, I think this is production in some different basis, maybe.
No. I mean, mixed separable states are just linear sums of product density matrices, and I think that's what you have as well. So maybe you don't need mixed state at each step.
No, I don't want a mix. I don't want just a pure state.
Okay.
So that I mean that's the definition of entanglement. I mean want to remove this entanglement structure. So what this unitary operation is doing is this just changing a kind of basis change from this. This is mix.
Yeah, that I understand. Yeah.
Yes. So that in the next step you do this get the pure state. So you can understand this unitary of disentangler as a change of basis state. So the disentangler unitary recognizing this state to prepare it for the coarse grain. That's what the disentangler actually doing. So
hi Pratik, I have a question.
Yes.
Yeah. So should I understand if in the there are two adjacent pairs and there is a entanglement inside each of these pairs, but your coarse graining is somehow taking the common link between these two pairs as a block, right? And hence you got entanglement.
Sorry, my coarse graining.
So you had R1 S1 entangled, R2 S2 entangled, but your coarse graining is now considering S1 and S2 as a single block.
Yes.
So then based on whether R2 S2 or R1 S1 had a plus bell pair or minus bell pair, you would assign it a pure state, like a single state. Your U does that. Right? That's what I'm understanding. You had a plus bell state in R2S2 system, and then you made it a 0, 0. I'm also a 0 or something. And I'm guessing if you had a minus bell state, you would have made it the other maybe 1, 1 or whatever.
Yes. So this is 1, 1. If you have a minus state, this becomes 1, 1.
So but I'm then confused. If there wasn't any entanglement in R2S2, would this procedure land me on a entangled state? I'm confused.
No, R1S2, this is not entangled. No, R1S2 is not entangled. So you only just you have this entanglement in only the nearest neighbor structure.
Yeah, but you can't check the state and apply this procedure, right? You are laying out this U procedure in the beginning, and then you're applying it to a given state. So I'm just asking, if there wasn't any entanglement to begin with in R1 S1, wouldn't this procedure land me on an entangled state between as in if R1 S1 had a state which was just 0 R1 and 1 S1, and then you apply this, how would you apply this procedure? Wouldn't you?
If I have an entanglement between R1 and S2,
if you didn't have any entanglement between R1 and S1 itself.
Okay. No, I am taking this R1 and S1 entangled, so I want to remove this entangled for the next step.
So I thought you will fix the renormalization procedure and apply it to any given state. You can't tweak it with given states, no?
No, I am taking this as some example. So I want to remove this entangle between R1 and S1 and R2 S2 before the course grading. So how do you actually do?
So you have to change U for a given state every time.
Yes, of course. Yes.
Oh, U is not fixed. U is not W and W dagger which were fixed.
No. This is for some example that I am giving this state. It may not be some different state also. Then U is different.
Oh, okay, cool.
So the thing is that you want your next step, you want a pure state. It's not a mixed state. So if you have some different state, then you will of course different. Yes.
So when I do RG, should I keep track of what U am I applying?
When I?
If you do the RG, do you have to also keep track of what is the U you apply? I'm just asking, would you keep track of U's? Like what is your prescription of U at each level of course grading?
Sorry, I didn't hear your question.
I'm asking, is the output at the final step is just a course grain state, or also what is the U you applied on the way reaching there? Am I making sense?
Can I phrase that question differently?
Yes, please.
Yes. At each step, do you have to look at which 2 qubits across the blocks are entangled and disentangle them? Or regardless of what state you have reached, you have a specific set of U's that will act.
Okay. I mean, this example is just for 4 spin, right? This example. So for a
not just that. It is an example with 4 spins, assuming that R1 S1 are entangled.
Yes.
You could also have like a separable state in R1 S1.
Yes.
And if you apply the same U, it would entangle that state. That you don't want that. So
Yes. So in that case, I need a different U. In different U in each step. Yes,
so before course grading, you have to keep track of like what qubits are entangled and then disentangled. Is that so?
Yes. But that is a very problematic thing, because in lattice I don't know actually which states are entangled and which states are not entangled. So
yeah, maybe Akhil can ask further if this was not his question.
Sorry, I just meant after you comment, I'm just asking, if do you keep track of U, like at the end of the RG and when you land on the course grain state, would you also keep track of the data of like what U you used on the way?
Okay, so the thing that we'll be talking
because I thought the way you mentioned, you said this though W dagger and W were in like inverses of each other, U dagger and U were inverses of each other, right?
Yes, they're inverses. Yes.
And so I'm just asking, would you be keeping track of how to go back up the RGE procedure?
Okay, so the things that we'll be talking about is actually called the scale invariant mirror. So that all the W's and U's are same. So one W user given, and things are just same. I'm just repeating this scale invariant. It's not a different W and different U are talking, but this what supposed scaling.
Maybe
I
can
can
show us an example. It will be clearer.
Maybe I can comment in the Slack, or maybe if you think.
Okay. Thank you.
Just,
yeah, I think we are already 10 minutes over time. So I think first let us all unmute ourselves and thank.
Just to think that these are due to this disentanglers, this postgrain doesn't accumulate this entanglement, and these isometries and disentanglers that we are talking about is the building blocks of this Mera and TNR that we next talking about this.
Yeah, let us all unmute ourselves and thank Pratik for this lecture. So since we have had already many questions, let me pause the recording and people can go on to ask more informal questions if need be. Okay, welcome back to the post-lunch session. Adwait will continue telling us about information loss problem in ADS2. Over to you, Adwait.
Okay, thank you. So let me start by reminding you what we have done till now. From the first lecture, we talked about the leading order. In the second lecture, we talked about the leading order state of the Hawking radiation, and we showed that if the particular structure which I described, that the new entangled pairs which are forming are not entangled with the old pairs, and also they're not entangled with the collapsing matter. And if you just assume this particular structure of the Hawking radiation across horizon, then you reach a paradox in a sense that you see that the entropy of the radiation keeps on increasing forever. Okay, and this is a problem because at first this is a problem because you'll see that at the end of the evaporation, when evaporation is completely done, the black hole goes away. The radiation of the entropy of the radiation is still some very large number, and that can only happen if the state of the radiation is a mixed state. So we started with some collapsing matter, which was a pure state, and then we saw that at the end we are reaching a mixed state. And this is a contradiction. I mean, this basically says that gravity is not unitary. After that, what we saw is that let's assume unitarity, and let's see what happens. Let me draw, let's see, a caricature of a cartoonish diagram where you have a horizon which is here, okay, and there are entangled pairs across horizon, okay, and they are going in and out. And then let's say at some end, after some time, you have corrected some radiation in this box here, and let's call this system R. And then there is some radiation, all of that which fell in, let's call, so there's some radiation here also. Now the point is, what is this Hawking process doing in time? The Hawking process, what Hawking process is doing is just increasing entanglement across this horizon. As pairs get produced, the entanglement across horizon keeps on increasing, and it just ever increasing. So the entanglement entropy of the radiation keeps on increasing, and what that says is the entanglement across horizon is just increasing forever. But we also know that this object which is sitting here, the black hole, has some coarse-grained entropy. So black hole has some coarse-grained entropy, and if I'm only talking about an eternal black hole, then that coarse-grained entropy is just area of the horizon divided by 4 pi g, 4 g Newton. Okay. Now, what is the problem? The problem is that this number, the coarse-grained entropy, is telling you that black hole only has these many number of degrees of freedom. Okay. So the black hole can only get entangled. The maximal black hole can entangle is when all of these degrees of freedom are entangled with something else, and that something else is radiation. But we are seeing that radiation just the entanglement entropy of the radiation keeps on increasing forever. But black hole simply doesn't have those many degrees of freedom to get entangled with. Okay, and that is the contradiction of page curve that we looked at yesterday, which was this particular graph. the graph here, what was happening is that we saw that this white curve here, which is the n log 2 answer, we saw that that answer is it just keeps on growing. But the coarse grain entropy is this horizontal red line. And at this point, the fine grain entropy of the radiation, which according to, so this point I should make clear that the fine grain entropy of the radiation, if you assume unitarity, is exactly equal to the fine grain entropy of the black hole also. Because we are assuming unitarity. We are assuming that there is a pure state which goes across from interior to exterior. Hence, if I divide that state at any point, the fine grain entanglement entropy of either side has to be equal to the other side. Okay, that's just from unitarity. So when I'm making this n log 2 statement, if I just assume unitarity, that's also a statement about the fine grain entanglement entropy of the black hole. Okay, so if I'm assuming unitarity, and if I have shown you that the fine grain entropy of the radiation increases, it also means that fine grain entropy of the black hole increases. But fine grain entropy of the black hole cannot be greater than the coarse grain entropy of the black hole. And we know what coarse grain entropy of the black hole, and it's just constant for eternal black hole. And that constant number is also proportional to area. Okay. So at some point, we reach a contradiction where the fine grain entropy crosses the coarse grain entropy. And that is the time we will call it page time. And that is where the paradox kicks in. Okay. And we don't know how to. So now I want to stay in the regime. I mean, I want to only start talking about eternal black holes, because eternal black holes, first of all, it's a best understood model of paradox. Second, that it clearly shows you that it has nothing to do with these things at the end of the radiation, and there's no, we never have to go to close to, with our slices never have to go close to singularity where there might be quantum gravity effects and all that. It basically says it's a smooth space-time always, and the paradox is very much in the regime where quantum gravity effects are neglected. It's called the midpoint. It's not literally the midpoint in time, but it's midpoint in number of degrees of freedom when they are getting exchanged. So that's why I like this model better. And also this is the most well understood model. So eternal black holes have this paradox, and we discussed about that. And today I want to start describing the ADS2 model. But before that, I want to review a couple of things which we will require in order to understand in order to do computations there, the similar computation, the n log 2 kind of computation. So let me start by introducing entanglement entropy 2D CFT. Okay. So
Adwait?
Yes.
I have a question which is based on this pair creation picture.
Mm-hmm.
So in this picture, it seems like the way black hole evaporates is through this pair creation.
Yeah.
And like as one member of the pair goes outside, one member also comes inside.
Yes.
Right. So I mean, I can't see, like, with such a picture, how will the black hole ever evaporate completely? Because you are creating a pair, and one is coming inside, one is going outside.
Oh, okay. Now I'm in the regime where I might make some wrong statements, but
okay.
Let me, yeah. The thing is, probably it's an antiparticle which goes inside, because the the space-time directions are reversed inside, and it goes and annihilates the matter which is inside.
Okay.
It's might be a very wrong statement, so let me not make a statement. Okay.
Okay.
Yeah.
I also have a question.
Yes.
In the case of the eternal black hole, I mean, as I understand, the paradox is simply because the radiation, I mean, you're continuously creating particles, and so therefore, I mean, there is increasing radiation as you go ahead in time. Yes. But in an eternal black hole, but the consequence of that is the horizon evaporates. Now, in an eternal black hole, clearly the horizon is the same, right? I mean, there's no change.
Yeah.
And
so in eternal black hole, we are so let me see if I have a diagram here. So if this is the eternal black hole, if the radiation at any point, I mean, if the radiation is escaping from here,
right.
It's coming out from the horizon. So
right.
It's also going in from this. So the rate at which we are feeding the black hole and radiation is escaping from the black hole is exactly the same. That's
Oh,
what
I
happens.
see. I see.
That's
I
why it
see. I
remains
see.
in equilibrium.
I see. Okay. Okay.
Okay. So, yes.
I have a basic question. So, I mean, I understand that this pair creation is what is causing this paradox in like at the core.
Yes.
But if I just consider just a piece of paper burning,
Mm-hmm.
then if I think of the radiation, I mean, thermal radiation coming from there, then the entropy of that will keep on increasing, and the information content of the paper is decreasing. So,
I'll tell you what the okay. I mean, these analogies are generally misleading because even if you have seen the string panel, they kept on talking about coal example, and everybody said, "Oh, it's not like a coal; it's like a coal." But let me tell you what I understand is the difference between black hole evaporation and simple coal evaporating away, or heated coal, is basically that coal has some atomic structure, okay, and coal is radiating, but every time when it radiates something, the state gets the updated state depends on, so nth the state at the nth time step depends on what was it at n minus 1 time step. So the whatever is emitted depends on what was the state before, okay. But in Hawking radiation, we saw it doesn't care about what the state was before. The structure exactly repeats itself. It's exactly the entangled pair, which is not entangled with old pairs and which is not entangled with the collapsing matter. So that's the difference. That Hawking state doesn't care about what is the state earlier. It just adds these pairs to the original state. But in coal, that doesn't happen. In coal, the updated state necessarily depends on what the state was there before.
Okay. You're saying that I mean, so like all the particles are entangled, kind of.
Yeah, the
with each other.
entanglement structure is quite different. As I understand it, it's not the same as Hawking. The Hawking's entanglement structure is very precise. It's almost puts a lot of constraints on these things. But maybe in but it's proved to be, it looks like that. So this anyway, let me say this, that this picture of pair creation is very it's to understand this intuitively, okay. So when we will actually do computations, our computations will enforce that this picture was correct, but the actual state is quite complicated. The actual, if I let me try to write down an example state, and that okay. So in this expanding cosmology picture, where where the, so if you just take, what you do is, okay, so what is the expanding cosmology? Basically, you have a metric which looks like this. This is supposed to be it plus dx square. Okay, so basically, and this a square eta is some function which looks like this. 1 plus some tan hyperbolic rho of eta. Okay, so what is happening is, so when eta is the time-like coordinate, when eta is minus infinity, you'll see that this m square is a 0. Okay, and when eta is plus infinity, it will is it 0? Yeah, it's a 0. And then when eta is plus infinity, it will go to just m square. Okay, so if I want to draw a graph, it will start from 0 and it will end up at m naught square. Okay, this is the protocol. So now what you can do is just take this metric, put a scalar field on it, free scalar field, massive scalar field, and try to solve for Klein-Gordon equation in order to see how fields are behaving in this expanding space-time. What you'll see is that you can solve this, first of all, with this tan hyperbolic function. You can solve Klein-Gordon. You can solve it for all times, but the modes are quite complicated. But what you can do is you can, so first of all, a Klein-Gordon equation is second order equation. So you'll get two solutions, two independent solutions. And you can write your field as some AK, and I'm writing it as U in, and you can also write it as, let's say, BK U, and I'll describe what in and out means. Let's see. Okay. So what does this mean is that you have found a solution. You have found two solutions, let's say, and the solution which at eta equals to minus infinity, the solution which at eta equals to minus infinity starts looking like e to the power minus I omega eta. There is a solution, one of the solution, let's call it psi 1, u1, that starts looking like this. And then I can, this is like plane waves. So it's plane waves at minus infinity. And then there is other solution which starts looking at e to the power minus I omega eta at plus infinity. Okay. And then that solution can be understood as a, so these are in and out. Okay. So one of them is the in mode and the other is out mode. And that's how what I call a particle is defined by these operators, AKs and BKs. And what I call a particle, that definition changes when I am, and that can be very precisely only defined at plus infinity and minus infinity. What is happening in the middle, we really don't know. Okay. So in that sense, the theory, the ground state of the, so how do you define a ground state? I'll define a ground state as AK acting on some 0 in going to 0. Okay. And at plus infinity, I can define a ground state as BK acting in 0 in 0, sorry, something called 0 out. Is equal to 0. Okay. And these necessarily are not the same thing, in the sense if I add AK on 0 out, it won't annihilate it. Okay. And precisely what is the relation between 0 in and 0 out? It looks like this. So 0 in terms of 0 out looks something like this. Half summation or K, gamma K is some function which we can find out, but I just want to tell you the rough form of the state. This operator acting on 0 out. Okay. This operator acting on 0 out. This is what it is. So now look at how the 0 in state, which is really at, I'm getting some feedback from somewhere.
Okay, I'll just mute my.
Oh yeah, sorry. So if you look at 0 in state, which according to AK in minus at my t equals to minus infinity, you would say there are no particles. But then look at that state in perspective of A out creation operator. So you'll see that it's an exponential operator. So let's de-exponentiate it and write it as 1 plus x squared. And then you'll see that always it acts on the out vacuum by two of these. So it creates a particle with k momentum, and it also creates a particle with minus k momentum. So one going in one direction, the other going in another direction. Okay. But there is a sum over k. So you could have this sum goes from 0 to infinity. I approximated it for just k going for 0 to 1, 0, 1. So two state system. And that's why I called it this thing. But this is the structure of the maximally entangled state that is really expected. Okay. So if you do perturbation theory and gamma, and if these states are just two state system, then you will see that what the approximation I was making is quite accurate. Okay. So what looks like a vacuum in past infinity, if you stretch the space time, and if you look at it future infinity, you'll see future time infinity, you'll see that the same state, it looks like there is it's filled with lot of particles. Okay. So this is what it means by when space time stretches, it creates particles, and it always creates these entangled particles everywhere. So okay, that's why the approximation is good. And there are some 2D dilaton models where you can exactly write down state in the context of black hole evaporation, and you'll see that the structure remains the same. So okay, so let me start talking about 2D CFT. So what we said was, if I generally want to compute entanglement entropy of a subsystem. So let's say I have a Hilbert space which has some HA tensored with HB. Okay. And I'm given a state on this all of Hilbert space. Okay. So what I really do is that if I want to find out, let's say, entanglement entropy of A, then I trace out the degrees of freedom of B from A, and this is how I obtain a reduced density matrix for A. And then if I want to compute entanglement entropy of A, I just compute the von Neumann entropy, right? So yeah, fine-grained entropy of rho A. Okay, this is the procedure, and this will be exactly equal to the fine-grained entropy of the system B, because this is a simple quantum system where unitarity is there. So now another way to obtain a fine-grained entropy or a von Neumann entropy. So von Neumann entropy is for a given matrix, for a given density matrix, is just minus trace rho log rho. Okay, and now what you can do is, instead of so in most of the examples it has been seen that computing this directly is quite hard. Okay, so what people do is that they compute this quantity. So let me call this is called nth Rene entropy, and nth Rene entropy, the formula of nth Rene entropy is this. It's log of trace of rho to the power n. Okay, and just assume that this rho is some reduced density matrix of some subsystem A. Okay, so the Rene entropy of that subsystem is given by this formula. Okay, and then entanglement entropy. So maybe I should write von Neumann here. Von Neumann entropy of the same object is given by is given by limit n tending to 1 of the Rene entropy. Okay, these are just definitions, but the point I wanted to make is that it's easier to compute rho to the power n and then take the log of that and then take this limit, than directly computing trace of rho log rho. Okay, and in most of the cases you want to do you would like to so in most of the examples I have seen, at least, that people do compute Rene entropies and then take n going to one limit in order to get the exact fine-grained von Neumann entropy. Okay, so this is one definition, and let's see how to do this in a continuum field theory. So here the intuition is quite clear. If you're thinking about qubits or just spin states with n-dimensional Hilbert space.
Adwait, I have a question. Like, what is the advantage of not directly computing von Neumann entropy, but starting from Rene and taking n going to 1?
I don't think there is any advantage. I think that it's just computationally easier to compute this quantity, to compute rho to the power n.
Okay.
Okay. Just taking nth power of a density matrix is easier than computing the above quantity. Okay. That's what but I don't think there's some inherent advantage in computing Rene entropies. Okay. Whatever I'm saying might change over the next few years, because these instant-on corrections, which I keep talking about in gravity, do really come from Rene entropies. We'll get that. Let me not jump ahead. So okay, so let's try to find out how. So let's go to the continuum field theories. So continuum field theory, and let's consider you're doing, and let's stick to the Euclidean picture first. See, it's safe to stick to Euclidean picture because we are not really doing any time-dependent computation here. And Euclidean path integrals or Euclidean picture is good enough to just talk about time-independent stuff rather than time-dependent stuff, because then you'll have to do analytical continuations and something might fail in analytical continuations. So okay, so let's just talk about Euclidean 1 plus 1 dimensional CFT. Okay, so there's no, okay, just let me write 2D CFT. Now take a space like slice, and let's say this is some coordinate tau, this is some coordinate x, and let's say you want to find out, and then this is, so it's just one-dimensional space, and what you want to do is you want to find out entanglement entropy of some sub-region here, and let me call this sub-region A, everything A else is A complement. Okay, So this is the, I want to find the entanglement entropy of this region. And for Euclidean 2D CFT, the answer to this is quite simple. And let me try to write it down. Okay. What should I do? This one. Okay, the answer to this looks something like this. It looks like the entanglement entropy of A, and I'll roughly try to tell you how it's done, but as long as if this formula is clear, we don't have to worry about all that. Okay, so it looks like this. How do I say it? Okay, so let me just write it. L by root of epsilon. So let me say that this point is x1 and this point is x2. Epsilon of x1, epsilon of x2, plus some constant. Okay, so let me try to explain this formula. So L is length of this interval. Okay, and that comes in here. So it goes as log of the length, but then what are these epsilons? So the point is, while computing entanglement entropy, it's not really clear. So if it's a spin lattice, I know exactly how to divide spins. I can just take 5 spins and then 5 spins. If it's a 10 spins, I can just divide spins. But in the continuum field theory, it's really hard to do this. It's really conceptually there's a problem, because how do you even divide? And people have seen, while computation in early computations of entanglement entropy, you always get divergences. These are UV divergences. So when you have to specify where you are cutting it, you have to specify to the smallest length scale possible. Okay, and from there you'll start getting UV divergences. So a consistent computation, which makes sense, of the entanglement entropy computation in continuum field theories, is always done with a cutoff. So you have to introduce some sort of cutoff. Okay, and that cutoff, what does that mean? So cutoff means I'm just saying that I'm saying that there is some smallest lattice spacing in my for my space. Okay, and let's call that spacing to be epsilon, and let's discretize our field theory according to this cutoff. This is a UV cutoff. Okay, we can do more general things. The more general thing being this, that let's say I have the same interval here, I have the same interval here, but so here, if you see, I've drawn these lines, this grid, equidistant, in the sense I'm just saying that cutoff everywhere is just constant. Okay, but now I can do something like this. I can say that, okay, maybe, right? So what I'm doing, I'm introducing cutoff, but I'm introducing a space dependent cutoff. Okay, so cutoff here is really space dependent. It tells you where I am, and a cutoff really cares about at what position I am. Okay, so I'm just introducing an uneven grid instead of introducing some sort of even grid, which I did in the first picture here. And these formulas, these epsilon of x, have entered in this denominator here. Okay, so in order to first of all get a sensible answer, you have to put a cutoff, and then you can do more general things like making the cutoff time dependent, and then that enters the formula like this. Okay, so I'll just stop for 1 minute. If you have questions, please do ask. There's something going on in the chat.
Madhu is asking, is this analogous to a smooth cutoff in momentum space RG?
Smooth cutoff in momentum space. I'm not sure actually, but might be related. I'll have to think about this.
What is the significance of the 1/3? Is it dimension dependent or something?
Well, it's 2D CFT. So this formula, whatever I'm writing, is only for 2D CFT.
Oh, I see. Okay. So then, what is the significance of the 3? I mean, is there a reason, or is it just some?
Okay. So okay, so let me just I'll answer your question, because I'm going to go to another interpretation of how do you compute these things, and then maybe something might be clear. We can come back to your question. But other than that, if anybody has a question,
could you repeat this smooth cutoff thing again? Like I didn't catch it.
No, I'm just saying that in order to get a exact see, in entanglement entropy, you are dividing your field theory into some subregions. So here I have divided it into A and A its complement. But dividing something along at a point in a continuum field theory is really, I mean, it's really not well understood. And the only way you can get some sort of sensible answers is if you do it, if you discretize it, and if you put some cutoff. Okay, basically make it into spins again, and then think about what is happening. Okay, so these surfaces are really called entangling surfaces. Okay, and how do you divide degrees of freedom in a continuum field theory across entangling surfaces is not very clear. But when you introduce a cutoff, it becomes slightly more clear. So you introduce a cutoff everywhere. So this diagram above is where I've introduced cutoff, which is uniform everywhere. Okay, it's epsilon. It's this width is, you can is always epsilon everywhere. But I don't really have to do this. I can basically I can basically convert it into an uneven grid. Okay, so let me say this way also. I'm writing, so this might be this might be bothering to somebody, that I'm working in a CFT but I'm introducing a cutoff. Okay, so the way, if you do a conformal transformation on your state, your cutoff also has to change according to that. So you can't keep your you can, if you want to understand conformal answers which don't really have any length scale, but then what you have to do is, if you have introduced a cutoff, you have to transform your cutoff also according to conformal transformations, and then your answers will make sense.
So I just want to sort of clarify that like the reason I'm asking this is because, I mean, you can work with like a strict fixed cutoff.
Yes.
I don't think there's nothing wrong with those calculations. I'm just wondering why you want to choose a position dependent cutoff, because I mean, what does this buy you is, I guess, my question. I mean, the reason I'm asking about this momentum space RG is because this is analogous to, see, if you have like a fixed cutoff, that's like saying that like above a certain momentum,
yes,
right, you're just all the momenta in the shell outside that momentum you're going to cut off, right?
That's true.
But you sometimes you don't want to do that. Sometimes you want to do it in a smooth way. So you have a profile function, right, which is one very far away from this number, and it goes to zero, like above this number.
Yes.
So there's a smooth way of doing it as well. So I was just wondering if this decision to have a smooth a space dependent cutoff, does that buy you something in particular?
So the thing is, okay, so does it buy you something? I don't know. I'm just saying that okay, first of all, it's just a generalization. If I put epsilon of x1 equal to epsilon of x2 equals to epsilon, then it'll just reduce to the standard formula. Okay, it'll be just L by epsilon, which I think a lot of people know. Second thing is that I'll be doing entanglement entropy later on in this lectures. I'll be doing entanglement entropy computations in bulk. Okay, in spaces like ADS, let's say. So ADS is conformally flat, but it has a while factor. Okay, so while factor is really locally changing cutoffs everywhere. So if I want to do real entanglement entropy calculations in the bulk,
okay, I see.
There the cutoffs are really changing everywhere because the metric itself has a conformal factor.
I see. Okay,
it'll be important there.
Yeah, that's a good answer. I feel, at least I'm satisfied. Thank you.
Yeah. All right. So let me go ahead, and here is where I come to the Anish question asked by Anish. Is that let's focus on computing entanglement, the third Rene entropy. Okay. So third Rene entropy. What do I have to do? Basically, I have to compute this object. Forget the formula. Okay. So I have to compute this object. So first of all, for third Rene entropy, I really have to first of all compute rho to the power 3. Okay. the formula, let me write one formula here again. The formula for enthalpy entropy is 1/1 minus n log of trace rho to the power n. So the main thing I have to compute is rho to the power n. Okay, and let's say this is for some subsystem A, and let's first start computing rho to the power n of the subsystem. Okay, it's a bit okay. Anyways, let's see. So these are 3 copies of 2D CFTs. Okay, 3 copies of 2D planes, where what I have done is that let's take a slice here in all of those 3. Okay, and then call this region in all 3 of them as the region A. Okay, these are all 3 are identical copies. All right. Now the computation of trace rho to the power A can be sort of thought of like this. Rho to the power, let's say I want to compute rho to the power 3. Okay, so what do I have to do? I have to compute something like this. I have to let's say let me call I, okay, not I, let me call it as phi I rho phi j as some rho ij. Okay, let's say this is some density matrix that let's say these are some basis states, and in which I'm computing this density matrix like here. Okay, and okay, let's go for the trace computation. So if I want to compute rho to the power trace rho to the power 3, I'm going to do something like this: rho AB, rho BC, rho CA. Okay, and then some more these things. Okay, so the and this is the trace rho cube computation. I'm writing the discrete version in order to intuitively understand it. And the other thing I wanted to tell you is that let's say I take a plane, and I want to tell you, and I do a path integral everywhere except a small slit here. Okay, I do a path integral everywhere, but except the small slit which I have left open. Okay, so everywhere else I have done a path integral, but I have not done path integral on this region in middle. So what is maybe I should say more about what open-ended path integrals mean. So if I'm doing a Euclidean path integral with some, okay, so if I'm doing a path integral which looks like this, let's say I'm saying phi equals to phi 1 to phi equals to phi 2 e to the power minus s of phi. Okay, this computes this object. It computes phi 1 e to the power minus I h t, whatever the contour here is in the action, phi 2. It's really computing a transition amplitude from a state phi 1 to phi 2. Okay, so let's say I don't tell you what the boundary condition at the upper end is. Then what is it really computing? What that means is that, okay, maybe I wrote it ulta. This should have been phi 2 and that should have been phi 1. So if let's say, what does that mean? I started at lower end with phi 2, and then I did the path integral, and then I stopped somewhere, but I don't know what the state is there. Okay, so it's not, now this computation is not really computing. So if I do this computation, it's not really computing transition amplitudes for me, but it's really just computing a state for me. Okay, and if I'm, depending on if I'm doing Euclidean or Lorentzian, I just have to change this I here. But just conceptually, I want to tell you an open-ended path integral, in the sense a path integral which does not have boundary condition, it's really computing states. It's not computing transition amplitudes. Okay, so when I was giving this example here, that I do a path integral everywhere on this plane, but I keep a small slit open, or this, okay, this slit doesn't really have a width. Okay, it's just a line. So this is an open-ended path integral, and it's really computing. So instead of computing, it is computing a state, but it's sort of computing a mixed state. Okay, in the sense this object is looks something like this: phi I, phi j, some density matrix like this, because it's not really that I have kept only one end open. I have kept really both the ends open. If the both ends are open, it's really a density matrix. Maybe okay, maybe we can I can talk about this later again, but it's not really that important to understand. But what you have to understand is when I leave something open in a path integral, it's computing states. Okay, and when I want to so it's really, so when this open-ended path integral is really computing something like this. Okay, and when I want to compute an object which is like row AB, row BC, and row CA, what I have to do is I have to glue. So I have to exactly take something similar. I have to exactly take something similar, and there is a slit here. But now, what does this multiplication mean here? There is a multiplication in these two. This thing, that multiplication really just means that I glue this side. I glue this side. Okay, I need a different color. Yeah. Did I change anything? So what I do is I glue this side of one copy to this side of the other copy. So you can think of as that. Okay, so let's think of this index as I, this index as J, and then this index as J, and this K. And then if I want to take a third copy, I'll again do the same, and I'll glue. Yeah, I'll glue this side to this side and call it K. And then again, I want to take a trace of this object, right? The trace of this object, meaning the last thing which is remaining here has to be glued with the original index here, and that is again I. All right. So this kind of a gluing really computes a trace row to the. So if I take n copies, it's really computing trace row to the power n. And what does gluing mean? The gluing mean that you're computing, you're creating a manifold such that if I go from, let's say if I go from here in this manifold, I'll exit from this side. And if I go from here in the lower manifold, I should exit from this side in the top manifold. Okay. So that's what the construction of row to the power n is. If you don't understand this, it's okay. I'm going to tell you something similar. So let me just rub this diagram on the right hand side. So so basically what I'm saying is that if I want to compute do computation of row to the power n of a particular subsystem, I have to cut my manifold along that subsystem. So our subsystem here was this length, this interval A. I have to cut it along that, and then multiplying different density matrices, in the sense this particular operation means that producing similar copies but gluing them across the cuts, and then tracing means gluing the last cut to the top cut again. Okay, and this is the replica trick. Really, this is the replica trick through which people compute traces of some row to the power a, row to the power n of some subsystem A. But there is a simpler version, and that simpler version is really nice. It's just that this is equivalent to doing this computation, that you just take one copy, and let's say your interval here is this interval A. All you have to do is that you do a path integral, but so here on this slice, you have to do path integral on 3 copies, or let's say if it's n, then you have to do path integral on n copies. Okay, it's an n-sheeted manifold, and the gluing means it's glued across those cuts, and then you have to do path integral along those things. But the equivalent representation of this is you just take one manifold, but you just put some twist operators. There are some special operators called twist operators, and they have an order, in the sense, let me call this phi n to the power phi n plus and phi n minus. Okay, so instead of computing this n sheeted object, you can just compute it on one sheet, But all you have to do is, while computing it in the path integral, you have to put these operators, okay, at exact points. So let's say now let me use the complex plane coordinates. So it's z1 and z2. So you have to put phi 1 at z1 and phi minus at z2. And what it really does is it creates a branch cut in here. It creates a branch cut of order n, so that if you rotate n times around any of these points, you come back to the same sheet, which is exactly the same that happens here. So if I go through this cut in the first sheet, I end up at the second sheet, then I end up at the third sheet, and after n times, I come back to the first sheet. That's exactly what's happening here. So computation of entanglement entropy in 2D CFT is really same as a computation. Rene entropy is the same as putting twist operators. Okay. So let me stop for some time and please ask questions.
Can you tell more about this twist operator? Like, is there those are some functions of like n square root functions, or?
The thing is, I have never seen a explicit construction of twist operators, but in 2D CFT, as long as I know a conformal dimension of a primary operator, I basically know everything about it. I know how to compute 2-point functions, 3-point functions, n-point functions. I mean, I should know OPs also.
Right.
So the point is, these twist operators are conformal primaries. And so basically what I said, that if I have a field and so if I go around these branch points, every time I should pick up a phase, and after n phases, it should come back to itself. Okay, so that kind of boundary condition for your field defines a OP of your field with this. So you can do whatever I said. You can do this for the stress tensor also, and the stress tensor defines an OP with your twist operators. And as long as if you know the OPs with this twist operators of the stress tensor, you can find out what the conformal dimension is, and then we are just computing conformal 2-point function with a conformal dimension which has an n dependence inside it.
I have a question.
Yes.
Sorry,
Akhil,
one second, Akhil.
Aruna had his hand raised.
Yes.
Yeah, so the previous picture that you were mentioning, in which you were actually identifying the surfaces for the n-sheeted case,
yes,
you had a slit which had a sort of width.
No, there's no width. It was just for representation. There's no width.
Okay, but so you don't take to t or t plus epsilon type of time slices. You take a single time slice.
Yeah. It's a single time slice. Yes.
Okay, so each sheet you have two sort of, it's connected to the upper and the lower.
So each sheet there is a cut, and that cut has like two folds. There's an upper. You can enter the cut from the lower side or the upper side, and that is what basically these two indices of the density matrix mean. There's an I and J. So I is something if you enter from the upper side, and J is if you enter from the lower side. And it's similar to saying that there is a state on the upper cut and there's a state on the lower cut, and you have not identified those two states. So these two are different states, and in that sense, the multiplication works.
So it would also be okay to just draw a one-dimensional line. You don't have to necessarily draw the 2D sheet because you are not considering any times changes, right?
Yeah, but in the sense, this is 2D CFT, right? So I hope I mean the clear calculation in 2D CFT, and I can always draw a line, but I would like to analytically continue these computations to Lorentzian signature.
Okay.
So at least all of these things which I'm describing are perfectly good when I analytically continue them to Lorentzian signature.
Okay. Thank you.
Hi. Can I ask this?
Yeah, your sound is a bit low.
Yeah, so I'm understanding this twist operator is just a nice name for doing this calculation in this replica way. Is that a fair statement?
I mean, it's a completely different technology, right? You're also doing a different computation.
No, I mean, I thought the twist operator is defined by doing this replica calculation, by going to some multi-sheet and joining it like this.
Twist op. Yeah, it's defined, but it's a conformal primary. I think it's just a perspective, but as long as you understand
So
what I'm saying, I think that's fine.
let me ask this. So if I had to calculate, if I had to calculate the entanglement of say two different disjoint cuts in the CFT, right, where I have two of these intervals, I would have thought I have to do a replica calculation like this, but in two places.
Yes.
Right. But the moment I think of it as inserting four operators,
yeah,
I will have to think about contracting them between the intervals.
Yes.
Right. And then I will have to connect replicas like that and so on. But that you won't do that if you have to calculate the entanglement of two different.
Oh, you would. I'll do it at some point.
You will do it.
Yeah. So this operator.
So you have to connect across the two intervals. That's not right. No, when you think about just matching the state across various sheets, you will. If I have interval 1 and interval 2. In each replica, I thought I will attach only interval 1 to the interval 1 dash, interval 2 to interval 2 dash, and so on. Would I attach 1 to 2
I'm actually
dash?
not understanding the question, but let's postpone this to Slack, or even after this lecture, I'll set for quite a while.
Okay, thank you.
So let's go that time. Okay. So this is the thing, and if I want to, let's say, compute an entanglement entropy of a plane with two different cuts, then it's basically a 4-point function where I have to insert four twist operators, and I'm always putting them in pairs as plus and minus, because you really need two of them and they really create a branch cut. Okay, sorry for this, somehow it's not writing in. Okay, so this is clear. Good. So let's go to the now let's go to the holographic entanglement entropy.
What's the difference between phi plus and phi minus? I mean, I know the name, that twist and anti-twist, but their conformal dimensions are the same. So why do we, like, what's the difference?
I think OP won't be the same, in the sense that one should pick up a positive sort of phase. One should give you a positive phase if you go around it, and the other should give you a negative phase if you go around it. So you might see this when you expanded the OP of phi with phi plus or phi minus with somebody else, you'll see a phase difference.
Okay.
Can I just make a remark?
Yes.
As an obvious distinction, they have cuts to the left or right. No, in that way they're obviously different.
Maybe.
So I don't understand. So you mean that phi plus will always be on the left?
That I don't think that's true. It's you can place
That's
phi
same
plus
as in they twist in opposite orientations. That's what I meant. You can look for whether the cut is towards the right of the operator or towards the left of the operator.
Could be, or just you can take it to be convention. Probably doesn't matter, because you can define the minus phase wala by plus and plus phase wala by minus.
Okay.
Anyway, so let me get to the quantum Ruthak energy, which is the most very important point. So let's say, and this here is one place where I'll start using ADS-CFT. So this plane here is your field theory, as I have already written, and this direction is the holographic direction. So you can think of this as the Z direction in your Poincare upper half plane. Okay, and the coordinates of this is X, and this is a spatial region. Okay, so all of this is a one space like slice through the bulk, whose boundary looks like this this plane here, the square what I've drawn, and the bulk is towards the right direction. Okay, now consider, so when I kept on saying in 2D CFT, in 2D CFT you just take a particular interval A. Okay, so if it's a high dimensional CFT, this would be some sort of a plane, let's say 3D CFT. So in 3D CFT, you have a 2-dimensional plane and one time direction. And then in that 2D plane, you can consider a subregion. And that's exactly what I have represented here, that there's a subregion in the plane. And let me call that subregion as B. Okay. And I can, by whatever techniques I had just told you, I can try to compute. So now when I'm in higher dimensional CFT, I don't have a technology of twist operators, because it just doesn't make sense. You have to maybe insert some sort of line operators. But I don't know if that construction even exists. But the replica trick should always work. Replicatrix just says you produce n copies and glue them across the boundaries of your regions. Okay, and then you compute the row to the power n, which would be just computing a partition function on this n-sheeted Riemann surface. So consider this to be some region B, of which you want to compute the entanglement entropy. Okay, and you can compute it from the field theory. But now let's try to see how do I compute this object from the bulk, from the ADS dual of this CFT. Okay, so what the prescription is this: you have to compute something. You have to compute a generalized entropy. Okay, which was introduced earlier. But you have to compute generalized entropy for a particular surface. It's not the horizon, because we could be considering states which doesn't even have black holes. So what does it mean by generalized entropy of a horizon? But you have to compute generalized entropy for a particular surface, and the first term in the generalized entropy is you have to compute area of that surface. Okay, and the second thing is that you have to compute S. I had called this, so let me write it below. I had called this contribution as S bulk, but now I'm going to write it as S semi-classical. Okay, what does that mean? Semi-classical means I'm computing entanglement entropy of a field on a curved background. So background is fixed, and I'm just doing quantum field theory on this curved background, and that is where and this is where I'm computing my entanglement entropy. So I have to compute von Neumann entropy in a region called entanglement wedge of the okay, let me start telling you the names. This chi is okay. Let's say this chi is some surface and sigma chi is some surface, and let me tell you what these surfaces are. So first of all, from the diagram, chi is a surface which is anchored at your region B. Okay, it's anchored at your region B and it extends into the bulk, and it's a co-dimension to all of the CFT. So let's say CFT is d-dimensional. Okay, do I do this? Yeah, CFT is d-dimensional. Then the region of the field theory I'm really considering, so this part is really d-1 dimensional. Okay, now the chi surface which I have drawn, which anchors at the boundary region, is also d-1 dimensional. Okay, is that clear? And then
sorry, Adwait, I don't understand this. You said your field theory, the field theory is your CFT that lives in d dimensions?
Yes. So there's an extra time dimension which I'm not drawing for all of these cartoons.
Oh, okay, fine. All right.
Okay. So there is a subregion here, and then the subregion is d-1 dimensional. Okay. So the boundary of the subregion, which is this black line here, is d-2 dimensional. Okay. So let me write something else. So the dimension of the region B is d-1. Okay. And the dimension of the boundary of B is really d-2. Okay. So the chi really the dimension of chi and the boundary of the subregion B is exactly the same because it's anchoring at that point. Okay, so the dimension of chi is also equal. So this is also equal to the dimension of chi. The dimension of chi is also d-2. Okay, so chi is a co-dimension 2 object. Okay, so this chi is a co-dimensional 2 surface. And what is sigma chi? So sigma chi is whatever enclosed between chi and B. So the blue region in my diagram is really sigma chi.
Adwait, is it that the dimension of del chi should be d-2, boundary of chi, or chi is itself dimension d-2?
Chi is itself dimension d-2.
Sigma chi is the bulk and chi is the boundary of sigma chi.
Right. So chi, sigma chi is a d-dimensional thing, right?
Mm-hmm.
No, sigma chi is d-1, right? Or d-1 plus 1. Yeah. So it's d-dimensional.
then chi is d minus 1, then dimension of chi should be d minus 1, and if the boundary of chi, which is del chi, should be d minus 2, is it? I'm not sure. Okay.
Just a minute. Okay, let
Sigma chi is
me
d
try to
minus
repeat
1.
all of these arguments. Okay, just to be clear. Okay, so okay, so if CFT is d-dimensional, then the dimension of the region B is d minus 1 dimension. That is clear, right? Because it's basically a space-like region in the d-dimensional CFT. So d-dimension means including time. Hence, a space-like region of that theory is a d minus 1 dimensional. Now, the boundary of this region, boundary of this B region is d minus 2. Okay. So another thing is that the sigma chi which I have defined, the dimension of that object is one dimensional extra than V. So it has to be again d-dimensional. Okay, so if you have a region B, union, am I audible?
Adwait, I think we temporarily lost you.
Okay,
so
I'm just saying this is just getting more confusing. I'm going to write down one equation and which I think should clear everything. So consider the region B, which is your boundary. If I take a union of that region with chi, that should be boundary of the bulk region sigma chi. Okay, what does that mean? That just means that I can continuously deform chi to B. Is that clear? So just remember this equation. We don't have to worry about what else happens. So in this cartoon, you can clearly see there's a region B on the boundary, and then there is a chi which anchors at B, but it extends into the bulk. Let's say if I shrink sigma chi to 0, chi and B would be exactly the same objects. Okay, so the boundary of sigma chi is B union chi. So okay, this is one thing. So in this formula, this is what you have to do. You have to consider surfaces chi such that the union of that surface with the boundary region you are considering should be the boundary of some bulk region sigma chi. Okay, now what do you want to compute? You want to compute the fine-grained entropy of the region B, but in the field theory. So okay, I have to start color coding stuff. What is the field theory and what is the bulk quantity? So let me start color coding it. Okay, so I'll whenever I write in yellow, that means that I'm writing a quantity that should be computed in a field theory, and whenever I'm writing in white, it means that I have to compute that quantity in the bulk. So a fine-grained entropy of the bulk region B, so it should be computed in the field theory, holographically is equal to this object. So this is what you have to do. So first of all, you take this S generalized formula for a particular chi. So you just pick some chi that you want, okay, which has to satisfy this condition, by the way. This is called a homology condition, that it basically says that chi can be continuously deformed to match with B. Okay, and this condition has to be satisfied by all the contender chi's, whatever chi's you are considering. So first of all, compute a S generalized for a chi. Okay, now do this. Now extremize over chi. Okay, so do an extremization problem. So vary over different chi's and extremize this object. Okay, and then it is possible that you might find multiple extremal surfaces. Okay, if you find multiple extremal surfaces, then you take the minimum one. Okay, so once you do this, whatever answer you get is supposed to be the fine-grained entropy of the boundary region that we are considering. Okay, I'll just stop for some time so that people can still ask questions if it's not clear. Or
I
I
have
can
a
repeat
question.
it again. Yes.
So when you introduced the fine-grained and coarse-grained entropies in your first lecture,
Yeah.
The discussion of the coarse-grained entropy was the one that involved looking at a bunch of contender density matrices and like
Yes.
computing. I mean, basically, you had to sort of there was a condition on them, right?
Yes. Yes.
So I'm a bit confused about why you're claiming that this is the fine-grained entropy. How do you know that?
I'm saying that this is a proposal. This is a proposal of a holographic duality. It says that if I want to compute a fine-grained entropy in the boundary, in the field theory, I have to do this procedure in order to obtain the same number from the bulk.
I see.
That's what it's saying. It's a proposal, and
I see.
it's very people have checked it in a lot of different
I see.
scenarios.
Okay, all right.
Happens to be true. That's why the left-hand side is really the fine-grained entropy, and the right. I mean, it should be computed in the boundary theory, and the right-hand side should be computed in the bulk.
I see. Subbu has a question. Subbu, go ahead.
Yeah, Adwait, are you saying this is not proved within IISc?
I mean, well, for some special cases, not in very generality.
Okay. No, because the original Ryo-Takayagi was proved, right? So this thing is not proved yet?
I mean, you're saying by this bulk replica tricks?
Yeah,
He's talking about Gaikwad-Smaldasina.
Yeah, but Gaikwad-Smaldasina is also a very special scenario. It's not the most general scenario, but I understand what you're saying.
Why is it special?
They assume some sort of U1 symmetry in their. So what you have to do is that they assume that in the bulk replica symmetry is not broken.
Okay.
That's an assumption.
Okay.
But maybe it's a reasonable assumption to make. Maybe.
Because so far it seems like very ad hoc to me. Like you just give me some quantity and say do this, and this, and this is a proposal.
Yeah.
I mean,
so these side of formulas also come from bulk. You can actually prove this, that from the bulk this is true, but you have to assume that the replica symmetry. So you really have to do. So whatever replica method I described, you have to do this with gravitational path integrals. And what people do is they create these n-sheeted surfaces with gravity in it, but you approximate the whole thing by saddle point, which we always do for gravity. And then but what is assumed always is that when you create these replica sheets, there is the solution that you get on. So you have to do a saddle point approximation for the path integral, and the solution that you choose is a replica symmetric solution. And there's no reason to assume that it's replica symmetric, but it gives you the correct answer. So maybe someone else has to prove that why someone thinks that replica non-symmetric solutions also should contribute. But that's something we can discuss later.
Okay.
So there is a question from Akhil. He's asking, could someone tell me what the difference is between a Ryo-Takayagi surface and this, as in the entropies they calculate?
Oh, so the thing is, this second term that I have added here is really correction over Ryo-Takayagi. Ryo-Takayagi was really just the first term. So if you exactly do whatever I said, but don't include the second term, only include the first term, then that surface will be called a Ryo-Takayagi surface. But now I'm starting to include, so the second term here is really a von Neumann entropy of the semi-classical fields living in this sigma chi region. So it's starting to correct itself by some quantum corrections. Hence it's quantum Ryo-Takayagi, not Ryo-Takayagi. And one more comment I want to make is that when I introduced generalized entropy in the bulk, when Bekenstein had written it down, he had only applied this formula for the horizon. And even then, it was what that formula was computing was a coarse-grained entropy. Okay. The point is, this formula cannot be applied to any arbitrary surface. It only has to be applied to it only has to be applied to specific surfaces, these chi surfaces, which come from this extremization minimization procedure. we'll call these quantum extremal surfaces. So the generalized entropy formula, if applied to quantum extremal surfaces, then and then only they give you fine-grained entropies. Otherwise, if you apply it to any random surface, it will start giving you coarse-grained entropies. That's in general, if you apply it to horizon, it's giving you a coarse-grained entropy and not a fine-grained entropy.
Hello, could you explain this minimization and extremism also?
Yeah, so first of all, you pick a surface chi, and you can pick a lot of these surfaces, but all of those surfaces have to satisfy this condition. It has to satisfy this that B union chi is a boundary of sigma chi. Okay, so sigma chi, roughly sigma chi is something that is trapped between chi and the boundary region. Okay, as the cartoon suggests. So you take that, compute it for a particular surface chi, and then you extremize over chi. So you vary chi and see at what point S generalized becomes extreme. Okay, so first derivative of that vanishes. So you find out where so you have to basically vary. You have to take different chi's. Okay, you have to take different chi's in the bulk. So I could basically choose this chi, or I could choose this chi. Okay, all of these are good contenders because they satisfy this condition here. So I can take all of these different chi's, but all I have to see is I have to compute S generalized for all of these different chi's and see at what point it extremizes. So if it extremizes, I pick those chi's. Okay, and it could happen that you get multiple chi's. So if you're getting multiple chi's, just take the chi, just choose the chi which gives you which minimizes over all of these S generalized over all of these extremal surfaces, and whatever minimizes the S generalized entropy for the chi will be called the quantum extremal surfaces, that particular surface.
Can one assume that even after minimization, one will get a single such kind of surface chi, not multiple?
Can one
like can one be sure that this chi is unique, like in a sense, even after extremization and after minimization?
I mean, what kind of scenario are you thinking
Means
about?
I'm telling like, okay, I don't know the scenario, I'm just taking mathematically, if one find two chi's and both chi1 and chi2, two surfaces, and both suppose minimizes this.
You're saying you're saying two surfaces which extremize and all of them, both of them have the same answer. I mean, there are two different surfaces which are also extremal and also same, so that they're also minimal.
Yeah. So maybe this is not possible. It's just I'm asking whether.
So the thing is, the prescription I'm giving you here is enough to make my points in future lectures, but there is a superior prescription which is called min-max prescription. Okay, and I think in that context, people have proved that these surfaces are unique, and people have also tried to, I think, conclusively prove that min-max prescription is the same as min-extreme prescription. Okay. So yes, I mean, I would say I don't exactly know the I don't exactly know the references right now, but it's Wall, Engelhardt, and Pennington. These people have worked on this, and yeah, that I don't know that is the answer, but I think it's yeah. Let me just say that.
Okay.
I have a question.
Yes.
So as I understand, if you wanted just the usual RT, you just take the minimal area of the surface chi.
Mm-hmm.
Right? And now if, let's say, I mean, naively, if I wanted to add contributions like this set generalized from fields living in the region bounded by this chi, you would just add all the fields within sigma chi. But here, what you're essentially doing is you're minimizing over a. If I do this procedure, I might end up with a surface chi which is different from the usual RT.
Yeah. You'll always end up with a different RT. I mean, they're slightly away from each other actually, because you see, the first term is 1 over G Newton, the second term is order 1. It doesn't have a 1 over G Newton in it. So it's like order 1 away from the. Well, is that true? It's not always true actually. There's a scenario which yeah, it's not always true, but in most reasonable cases this is true, that RT, the statement that is true is RT and QRT are always different surfaces.
Okay. I see.
Unless the semi-classical contribution is very trivial, and it's a zero basically. If it's trivial, then you have no contribution, and then RT and QRT will always be same. But if the bulk fields are doing something non-trivial, then you will have some. Then these two are necessarily different.
I see. Okay.
Okay. So yeah. So this is good. And let me say some words about entanglement wedge reconstruction. So what entanglement wedge reconstruction says that, let's say you have some operator which is localized in the bulk, okay, and not localized, it's in the bulk, and you want to, so ADS-CFT, according to ADS-CFT, you would expect that, well, if there is some operator that is written down in the bulk spacetime, I should be able to construct it from the boundary operators. Okay, I should be able to write down a complicated function of boundary operators, which does which is exactly same as which does the exact same job as putting an operator in the bulk. Okay, this procedure is called bulk reconstruction. We have also had lectures on this in last year's ST4. But now the only words I want to say here is that if you want to reconstruct an operator in the bulk from a sub-region in the boundary, it can be only reconstructed if the operator sits in the entanglement wedge of the boundary region. Okay. Now what is an entanglement wedge? So entanglement wedge is the entanglement wedge is sigma chi extremal. Okay. So you do this procedure here and you find out what is the extremal surface. So you found out some extremal surface. So for that extremal surface, there's going to be a sigma R region, sigma chi region. Okay. That sigma chi region in the bulk is called the entanglement wedge of the boundary region B. Okay. So if I want to reconstruct an operator in a particular bulk region, I can only reconstruct it from a boundary region in whose entanglement wedge whose entanglement wedge covers that particular bulk point. Okay, so this is a very very lame explanation of what entanglement wedge reconstruction is, yeah. So this is it, and then you can assume that. So let me draw
Question?
some. Yes.
I'm curious. Why didn't you say quantum RT? You said sigma extreme, because there could be multiple sigma extremes, right?
There, well, not really.
Why do you have a min operation outside the sigma extremal when you define quantum RT then?
Well, see, this is the proposal, so just take it at face value and run with it.
I'm just asking which sigma extremal.
I'm sorry. I'm calling it as extremal surface, but the extremal surface is something that you get after doing all the procedure, extremal minimal procedure. Okay, sorry. This is
you meant quantum
yes,
RT.
I'm quantum. Yeah, a quantum RT surface. So, okay. So if chi is a quantum RT surface, okay, then the sigma quantum RT is sigma chi quantum RT is called the entanglement wedge of the region B, the region B that we were considering, and this particular relation will always be true, that B union quantum RT will always be the boundary of sigma chi QRT. Okay, now let me draw, so this is an ADS, okay, this is a disk, and let's say there's some operator here, and I can choose a subregion on the boundary, and I can construct a QRT surface for it, and it will look something like this. So this is my subregion B, this is my chi QRT, hence this region in here is sigma chi QRT. Okay, so if I want to construct an operator which sits in here, I can construct it using using the operators only lying in the region B. Okay, but you could also construct different entanglement. So you could consider, let's say, I don't know, you can consider this region here. Okay, which is so something like this. And the QRT surface also might keep the, so the QRT of that particular region. So let's call this region A. The quantum RT surface of A also might include that particular bulk point. And now it says that, now according to entanglement reconstruction, it says that I can also reconstruct that operator using all the degrees of freedom, or using all the operators which only lie in A. Okay. So the point I'm trying to make here is that a bulk operator can have multiple boundary representations. Okay. Multiple regions, subregions in the boundary can reconstruct the same operator if the same operator lies in their entanglement wedge. That's one point. And I think that's fine. I have 10 minutes left, and where do I go from here? Okay, fine. So this is good. I really wanted to start.
Can you revert your statement to say, like, changing the same bulk operator can affect the CFT in different regions? Does that make sense?
I didn't understand.
As in, like, if inserting an operator where you had the red dot in the bulk is equivalent to inserting an operator in the region A or B in the C and
No,
B.
no. So okay.
Is that right? No.
Inserting an operator in the region. Sorry.
Say bulk field operator in the region red will equivalently have changed the region A and B in the. That's not right.
No, see, no, that's not right. I see. I just want to represent a bulk operator using all possible combinations of boundary operators. So I can choose, if I choose all boundary operators, then I'll always be able to do it. But let's say I only want to do it using a subregion in the boundary. So I only take a subregion and I only take operators which are restricted to that subregion. So I would only be able to reconstruct the operator in the bulk from that subregion if and only if the entire that particular point in the bulk lies in the entanglement wedge of that subregion. That's the question.
Okay.
So okay, with whatever time I have, let me just very quickly. I don't know whether I should start this. Let me see if I can tell you something else. Yeah, anything I have will take a lot of time, so I don't think I want to start anything new. But okay, let me just tell you about JT gravity, because you don't really need JT gravity at all, but just to know what model we are working with, it might be helpful. So JT gravity is this. JT gravity has, and it's really 10 minutes, it's not more than that. So JT gravity has 3 terms, and I write these 3 terms as this. And if I want to add, I can add matter. Otherwise, I can't. It's okay if you don't add matter. You can work with pure JT. Okay. So this S topological term looks something like this. So it has a constant sitting here, phi naught, for 16 pi g. Why am I writing so big? So you have S topological, which is minus phi 0 16 pi g. And it has these 2 terms. So it has, so we are on some manifold, and it has the bulk term, which just looks like root gr, plus a boundary term. Okay, so the boundary coordinate I'll call u. So there's a du coordinate, and this is the boundary term, and that term looks like root gamma k, where root gamma is the induced metric on the boundary, and k is the extrinsic curvature of the boundary. Okay. Now this is in 2 dimensions. Okay, in 2 dimensions, this is just this is like Einstein's gravity term, and we know that Einstein's gravity in 2 dimensions really trivial. There's nothing in it. So why do I say that? Because by Bose-Garnet theorem, I can say that this object is just I can do this integral on any manifold, and it will just give me this answer. Okay. And what is chi of m? Chi of m is really Euler character of my manifold M. Okay, so this is Euler character. Okay, Euler character is I think 1 minus 2g, where g is genus. Yeah. So chi is.
Sorry, it's 2 minus 2g.
Yeah, sorry. 2 minus 2g, where g is the genus of the manifold. Okay. So hence the topological term is really topological. It really has nothing in it. It just counts it just counts the genus of what manifold we are working on. Okay. Now let's come to the interesting term. The interesting term is SJT, which looks like this. So it's 1 upon 16 pi g. Yeah, let me put a bracket here. On the manifold, which is a 2-dimensional manifold, I have root g, and I have the phi, the dilaton, r plus 2. I'm setting the length scale. Okay, let me for once write down the ADS length scale. So it looks like this, plus 2 into, now I'm writing the boundary term on the boundary, and that boundary term is also contains the phi. But now I'm going to introduce, I'm going to slightly modify the boundary term by this -1. Okay, so this du here is a boundary coordinate, gamma here is the induced metric on the boundary, k is the extrinsic curvature of the boundary, and that -1 is really something called the counter term for the renormalization. So what does that mean? That means that if I take a solution and let's say I want to do a path integral of the gravity, okay, and if I want to do a gravity path integral, no one can do it. So what you have to do is you have to just do a saddle point approximation, in the sense that find a solution and find out what is the action for the solution, and e to the power minus s, e to the power minus action is the approximate path integral that you have. It might happen that if you put a solution into your, so this happens typically for black holes. So if you put a black hole solution into your action, the action will just go to infinity. Okay. And you need to you can add some local counter terms to your action in order to renormalize it, in the sense, in order to make it finite when evaluated on a particular solution. And that's why I've added this -1 term here. It represents some sort of volume contribution. So if you remove that volume contribution, everything becomes finite. So okay, so this is what we have, and this is the JT gravity. So let me see how much time we have. Okay, let me also tell you what are the equations of motion. So if I vary g, okay, the equations of motion from g. So we'll always forget the topological term. We'll always say that topological term gives me, so it's a constant that sits outside the path integral always, and it just counts what the genus of the manifold that I'm working with. So the second term here is the important term. And if I compute the equation of motion for the metric, that equation of motion looks, is it really important? Yeah, that equation of motion looks something like this. Minus g mu nu del square plus g mu nu by L square acting on phi, which is the dilaton, and right hand side would be, okay, I don't exactly know the constants, but it's some g Newton and T matter. Okay, and T matter is something that you just can find out from the term here. So this is the equation of motion that comes from G, but mostly we'll assume that there is no matter. Okay, I'll tell you in what sense there's no matter, but let's assume that there's no matter. Then it's just this equals to 0 is the solution. And if I vary phi, that gives me r plus 2l square equals to 0. Right? Yeah. Because you can see that phi is just it's just a linearly multiplied to r plus 2 term here. Okay, so if I verify, I'm just going to get this. Okay, now this, so you can see that whatever we get in general, similar to the Einstein's equations, g mu nu is equal to 8 by g t mu nu, is really this term, is really the g equation of motion here. Okay, and if you look at phi equation of motion, it just gives me r plus 2 by L square equals to 0. Okay, so metric, so you can see that this equation completely tells you what the metric is. It tells you that the curvature is locally negative, and that negative number is 2 by L squared. Okay, and Shubhendra, I'll need maybe 2 or 3 more minutes just to complete
sure,
this
no
thought.
problem, no problem.
So if you look at this equation, which is r plus 2 equals to 0, that just tells you that your manifold is locally ADS everywhere. Okay, and that is all there is in the metric. Metric is completely determined by this equation. Okay, because if you do some gauge fixing, and if you try to find out asymptotically ADS, so you can just assume that it's just Poincare ADS2, let's say, or global ADS2 everywhere, because all you have to say is metric is locally ADS2. The point I'm trying to tell you is that there is no degree of freedom in the metric at all in 2D gravity. 2D gravity, in this dilaton gravity, Jakob-Teitelbaum. But whatever is the essence of, whatever is the essence of dynamics in the bulk is really captured by the dilaton. Because you see, dilaton is something that back reacts by, that takes account of back reaction by the matter, but not the metric. So I can always assume metric is something, I can always fix my metric to be something, and all I have to see is whether this particular, the first equation that I've written here is satisfied. So there are no, I mean, you can't ever see anything back reacting on the metric. So metric never changes. Metric always remains what it is. So metric, in the sense, traveling gravitons is not a degree of freedom in 2D gravity at all. There are no propagating gravitons. But there's a scalar field dilaton which captures those essential things. Okay, and we can reduce this to something more minimalistic. Is that what is the real degree of freedom in this theory? The real degree of freedom in this theory is that where you place the boundary. So the placement of this boundary manifolds is the real degree of freedom. Okay, because let's compute an action. Okay, let's say let's say I'm looking at different configurations of metric in higher dimensions, and I look for what are the contributions of each metric by looking at how much action do I get for each of them. If I start doing it here, all the metric should give me the same action, right? But that's not true, because there is a non-trivial boundary. So where you put the boundary will change the action. Okay, and if it changes the action, these are non-trivial different configurations that come in your path integral. Hence, the real degree of freedom is where you place the boundary of this manifold and not the manifold itself. Okay, that's what I wanted to convey. And yeah, maybe.
Sorry, just a question. This phi naught is the boundary value of the field, right?
Phi, sorry?
It's phi naught.
Phi naught is not the boundary value, sorry. Phi naught is just some constant that sits in the topological term.
Oh, okay.
So basically, these Jakob-Teitelbaum gravity can be derived from so by the way, I'm done saying. So if you have questions and if we have discussions, we can start that. So phi naught. So if you can get these theories by reducing from higher dimensions. So you have to start with a near extremal black holes in higher dimensions, and if you do a near horizon reduction, you'll get this theory. You'll get the S topological term, and you'll get SJT also if you truncate it close enough to the horizon. So phi naught is really the area of the extremal horizon, horizon of the extremal black hole in the higher dimension. But in lower dimension, it's just some constant that's sitting there. Okay, I'm basically done. So
okay, let us Anish, let us first thank Adwait.
Yeah.
Yeah, please go ahead with your questions, Anish.
Yeah. So why, I mean, given that there is no fluctuating gravitational degrees of freedom, why is it still called gravity? I mean, maybe it's a very naive question. Isn't it just some scalar field on a gravitational back? I mean, on some curved background.
Yeah. So I'm just saying that scalar. Okay. So what I wanted to convey really is that the only degree of freedom is where you place the boundary. Okay. Where you place the boundary. I'll get to it in next lecture very clearly, that how only where you place the boundary is the degree of freedom. but where you place the boundary is important. And another thing I wanted to say is I showed this example as an on-shell, as an equation of motion. Okay.
Right,
but
right.
It's really not an equation of motion, because if you think about doing path integral of the phi field, you will really produce a delta function of this object in your path integral.
I see. Okay,
Right?
okay.
Because it's just a linearly multiplying, and if I assume that phi is integrated along a purely imaginary axis, then it's producing a delta function. So r plus 2 by L square is really an off-shell condition. It's a condition on all possible off-shell configurations. So it just fixes the metric. So the only thing that can differ in off-shell configurations is where you place the boundary. And that's why the gravitons in this 2D theories are called boundary gravitons.
I see, I see.
Right? So that's the only degree of freedom. But if you put an extra scalar field on this, so the thing that we were putting here, the S matter, they can travel. They can travel on this background, and in the classical limit, you will see that the back reaction of this matter is captured in the dileton and not on the metric.
I see. Okay.
And it is tightly tied to the boundary manifold, but I have to come to that. It's a subtle, subtle connection.
Okay.
Any other pressing question?
Yeah. Could you tell me once more, where did this Klein-Gordon-like equation come from? Was it varying the G?
Yeah.
And that's proportional to the T mu matter?
Yeah, I mean, I have some matter up here, right?
I'm confused because on left side, it kind of looks like it's linear in field, and the right side is...
Oh, wait. How do I say? See, the S matter, so let's call matter as chi, some chi. Okay, chi, I don't know what is. Okay, let's call it F. No, let's call it chi for now. So this S matter is chi. Is the stress tensor that comes from this chi fields, and this phi here is dileton. Does it make it clear?
Okay. Thanks.
Okay, I think it's 6 minutes past 4. Let's thank Adwait again. Okay, welcome back to the last lecture of today. Parthiv is going to continue telling us about S-matrix Bootstrap. So what do you, Parthiv?
Okay. So let me just, in the last lecture, we discussed some analytic structures of the S-matrix, the scattering amplitude, which is of course very vast, and it's very difficult to do any kind of proper justice to it. Nevertheless, let me just start by listing down all the important analytic structures that we're going to, that we anyway need apart from the stuff. So first one is the so-called real analyticity, which really tells you that the T star, so the scattering, the complex conjugate of the scattering amplitude is the same as the scattering amplitude with the Mandelstam variables S and T itself conjugated. Then there is of course crossing symmetry, which tells that TST, for example, is equal to TTS, and I have not bothered to write down all the other U channel kind of stuff, but essentially everything is crossing. The other thing that we will take is this so-called rigid boundedness, which really tells you that for fixed T, there exists some domain in C2, and C2, I mean, it's basically a completion of C2 with infinity, where mod S is bounded by, mod T, the modulus of T is bounded by mod S to the power some J naught, which is a function of T. When S and T belongs to this domain, this domain also must contain the point at infinity. And the last bit about this is this what is known as maximal analyticity, which is a strongest analysis assumption, and even within the context of axiomatic field theory, it's not been proved. So what it really tells that this scattering amplitude is analytic in situ, except possible poles corresponding to stable bound states, and of course in all the three channels, and of course the obvious threshold branch cuts. Now we are assuming there is no resonance actually for that matter, because well, even resonance, last day we discussed resonance is also pole, only they are not poles on the real line, but also only in the lower half plane. However, for our purpose, we will not really need the maximal analyticity anyhow, and we will only need some kind of extended analysis kind of stuff. So all we need is that there exists some domain belonging to the C2 where TST is analytic, except for possible poles. We will not even go to the pole. I mean, we will not consider even poles, and the threshold branch cuts is greater than 4m squared, and their images under the crossings. So these are the important analytic structure that we will need anyway. So that's all we'll do. Now, so far so good, but
let me ask a question.
Yeah.
I think you made some modification compared to the last lectures in the first slide. Like there, yesterday you told that it is bounded like s square for fixed t. Now you are making it a statement like it goes like s to the power j0 of t. So
yes, yeah. I would say that but even then, I think we will see there isn't this assumption that I think that J0 is greater than 2 or something, greater than equal to 2 actually.
Okay, so your J0 will be always less or equal to 2.
Yeah. So I think in my opinion, the Rege boundedness a little bit stronger than that only polynomial boundedness kind of stuff. Okay. So with all this analysis structure, whatsoever, had my advisor would have been here, he would have asked me, okay, so far so good, but what would you really do with all these things? So we will actually do something. I mean, we can of course do a lot of abstract stuff, but what can we do which actually matters? And this would have been exactly in those words. So what we will do is a large expansion. Now, large spin expansion is by now it's very regular in the conformal bootstrap program. There's been immense exploration for that. We will also do a similar kind of large spin expansion. Only the concept of large spin expansion is not new in scattering amplitude, and this I came to know. This even I did not know, but this I came to know in Zibowedov's paper, where apparently in 1960s already there was also some concept of large spin expansion. Of course, the large spin expansion in the conformal bootstrap program were developed, independently of these things. Only the style in which we are going to study all this. So, large spin expansion will be our final goal of this lecture, and possibly next lecture and up to the penultimate lecture, perhaps. And we will develop whatever is needed for doing this, for having this large spin expansion. So, the starting point of this entire discussion on large spin expansion is the Frossard-River formula. So, Frossard-River formula starts from the partial wave expansion of the scattering amplitude, which is this. So, here I have written this cos theta z equal to, and of course, this is identical particles of masses m. This is equal to 1 plus 2t by s minus 4m square. Now, using the orthogonality of the Legendre polynomial, I can write down these partial wave coefficient, this FLS, in this following form. So, just to remind, the Legendre polynomials are
Parthiv, if I remember correctly, the Froissart-River formula that you wrote down in the previous slide, I mean, earlier you told that that was only for non-spinning, I mean, the scalar particles, right? So
no, I did not write in the Frossard-River formula. I just
Okay, sorry, then I'm mistaking. But this T that you have written down in this partial wave expansion, so this contains also spin, meaning information about spin of particles.
Yeah.
Okay.
Yes.
I mean, so where in this L you mean?
No. This is just scalar boson, or the case we are being considering, like identical mass scalar boson. So I think I also wrote that expression only previous long back.
I see. Okay.
Okay. So just to recall, this is we have used the orthogonality of Legendre polynomial. Okay, but here is a point, and this has to be, I think, this thing we need to mean. This expansion. So on the right hand side we have an expansion in terms of PLZ, and on the left hand side we have a function. Of course, it's an important point that one has to have, for this formula of this FLS to work, one has to have a domain at least in the complex Z plane. So I will be looking at in the complex Z plane where this expansion has to converge. So there should at least exist a domain to start with in the complex Z plane, so where this expansion actually converges. And the answer is yes, there exists a domain in complex Z plane where the expansion converges. Now, this I could not discuss in details, but let me just tell you the result, that there's a domain called Lyman ellipse. So, okay, it's not just Lyman ellipse, it's small Lyman ellipse. It's small Lyman ellipse. So, Lyman proved that there exists an ellipse having foci at ±1 such that T is, okay, so this is in Lyman, T is analytic inside the ellipse in complex Z plane for is greater than, of course, is greater than 4m square. So when he proved it, of course, he did not prove it. He did not consider any Legendre expansion or whatever something. He did prove it in the most general scenario that there exists an ellipse with foci at ±1 in the complex Z plane for is greater than 4m square, where this TSZ, that means the right hand side. The right hand side is actually analytic. Now, it is interesting that just as for power series, for any arbitrary power series, the convergence domain for the geometry that is played in the convergence domain is a circle. For any Legendre, this kind of expansion in terms of Legendre polynomial, this convergence domain is of this elliptical side, elliptical shape. So what I really mean by this is that, that if I have an expansion of this form, then this converges inside some ellipse with foci at ±1. From Lyman's work, we have one such ellipse to start with. Thus, it is within this ellipse our work begins. So this formula, this FLS we could write in a domain. I mean, if I just, even if we are integrating over -1 to +1, but this is lying within that ellipse, so we are actually being able to write this kind of stuff. The basic thing about Frossard-Griefer formula is we really want to go beyond this ellipse using some kind of extended analyticity. Some kind of extended analyticity. The starting point now, in order to do that, what we will need is another, it's what is called Legendre function of second kind. Now this is the second solution of Legendre differential equation. Just to write down, this has an representation in terms of hypergeometric function. Which is valid only for mod z greater than 1, because anyway, this it's very clean to see that this hypergeometric function converges for mod z greater than 1, and also it's defined on the branch argument of z less than pi. Now, this function is related to Legendre polynomial in this way. So Fn minus 1z, where Fn minus 1z consists of only non-negative integer powers of z, and n is positive integer. I mean, positive integer and 0, of course. So what does it tells that Qnz as branch points at z equals to plus minus 1. But not only that, it has the property that for z belong to -1 to +1, so this is an important relation that we are going to write. So what it really tells is that Qnz has a branch cut. has a branch cut structure between -1 and +1, and the discontinuity across that branch cut is related is actually proportional to Pn, the Legendre polynomial. By the way, n here always positive integer. I should also mention, because this will come later handy later, that there's a Newman's expression of Q and Z as an integral over P n Z minus 1. So one can also prove that above this discontinuity relation from this integral representation simply by using that 1 by z minus y and using that usual Feynman kind of stuff that we do anyway. So whatever the important thing is that it is this expression of discontinuity of Q and Z in terms of P and Z. This is the most important bit for developing the Frost-Hilbert formula. Now,
so Parthiv,
yes,
this value of Z between -1 and +1, that still lies within the Lehmann ellipse, right, or beyond?
Yes. It is because the Lehmann ellipse is an ellipse with foci at +1 and -1. So essentially, that segment is still there.
Sorry, I couldn't understand. Parthiv, are you there?
Yeah. What? Yes. Hello. Yeah. Can you hear me?
Yes, I can hear you.
Yeah. So what I'm telling is that the Lehmann ellipse is an ellipse with foci at -1, +1, and some, of course, I mean some semi-major axis which is greater than 1. So it's still within that domain.
Okay, so when you introduce this Qn of Z, then only you go beyond to the Lehmann ellipse. Is that
Yes. Because Q and Z, I mean, so Q and Z is the only singularity structure for Q and Z is in this within -1 and +1. Now we will see that outside that Q and Z does not have any issue. So we will exploit that thing shortly. Okay, so let me write down let me once again write down the formula that we wrote. Sorry. So we wrote this as pi to 1 L set T S set. So in the complex Z plane, +1, and okay, let me just so now for Q and Z, we have you have a branch cut. So this is for Q and Z. Now you can use this relationship, this relationship into this expression of FLZ. Now, when you do that, so what does it? In doing so, what you can do, you can write down this FLS as
Parthiv?
Yeah.
In the chat, Pinaki is asking, like, if you can summarize in 30 seconds, what is your goal here?
Oh, so right, I will actually derive the Frost-Hilbert formula where this FLS. So no, ultimate goal is to derive the formula, but so right now what I'm trying to do is I'm trying to go into this an integral in terms of QS. So ultimately, we want to write down a formula for FLS that can be analytically continued in L.
Okay.
Did you say analytically continued in S?
No. Why we are not analytically continued in S here? S is fixed for some for S is greater than some for m square.
No. Could you repeat again? What did you say is the final aim?
So I will be one of the so Frost-Rickenbacher formula, for example, is the starting point for Regge theory. So one of the goal of the Regge theory is that in Regge theory you want to analytically continue in the spin. So that you cannot do in this original formula because there you are using only Legendre polynomial and which is only defined for integer n. That's why I'm going to introduce a function. We are introducing a function which can be analytically continued in L.
Can I ask something?
Yeah,
okay.
yeah.
So in this partial way only, if you have replaced the formula for replace PL with the hypergeometric, some hypergeometric which represents PL, couldn't I just analytically continue the hypergeometric arguments?
No. Partly because of the fact that, well, if you can still do it, but it will express things in terms of this TSZ. But if the final formula will express this thing in terms of discontinuity of TSZ, which is much more accessible than the usual amplitude. Usually the discontinuity of the amplitude is much more accessible than the amplitude itself. Even in the experiments, by optical theorem, you know, from scattering cross section, for example, forward scattering cross section, something like that, you know, that it's because in some sense, just be honest that the discontinuity is less it's more easily accessible than the amplitude itself.
So
most of the task is
go on, sorry.
Most of the task is done with respect to, for example, discontinuity of the T.
Okay, thank you.
Okay, if you do that, so this contour is now over which you are actually integrating. Of course, as you can see, this upper is of course corresponds to z plus I epsilon, lower is corresponds to z minus I epsilon, as minus 1 plus 1. Okay, fine. So now you go to the full. So this is just expressing in terms of plus 1, and now we are assuming that there is no bound state. But
Parthiv, now effectively this diagram you are drawing is really a complex T. Like earlier you were trying to look at the branch cuts and all these things complex S, but now you are fixing S and looking at complex T.
Yes,
roughly.
Yes. Yeah, right. Yes, yeah, exactly. I'm now seeing this whole stuff in complex. So now S is real and assumed to be greater than 4m square, and that's fixed. And looking at for that S, I'm just going to I'm looking at what are the corresponding A structure in the T complex T. So you can have a similar. So for example, here Z naught corresponds to the threshold in T channel. Which you can actually very easily calculate from, for example, using the formula. So using the expression for Z equal Z. So just you put this Z naught is actually equal to 2 times 4m square S minus 4m square. S is greater than 4m square. So Z naught corresponds to the T. So for fixed S, Z naught corresponds to the T channel threshold, and minus Z naught, Z equals to minus Z naught would correspond to the U channel threshold.
Sorry. So Z naught is a
yeah. Sorry. Hello. Sorry, I'm not listening anything. Hello.
I think we lost him, so you continue. If he comes back, he will ask the question.
Okay. So yeah. So okay. Next, what we are going to do? We are going to blow up this contour. Of course, we have not assumed. We have assumed there's no bound. There's no bound state. So if we blowing up this contour, we are going to blow up in this fashion that. So let's set the color.
Hi, Parthiv. I have a question. Can you hear me?
Parthiv, are you there?
Yeah, I think we lost him. I mean, his name is there in the participants list.
Yeah. Yes.
So maybe you should start from 41st slide.
Okay. So where was I? Yeah, 41. Yeah. Okay. Yeah.
I think 40 slide. Yeah.
Oh, 40.
40 we lost you.
Okay. So 40 slide you have seen. So 41. Okay.
Yes. So in the 40 slide, I have a question actually.
Oh yes. Yeah.
So in the slide 40, when you are deforming this contour away from this -1 contour, like you know that in the FL expression you have not only this QL of Z, but also you have this T of S, Z, right?
Yes, just a second. Yeah, right. No, now I have QLZ and TS. So
exactly,
this is
Q and T, right? Now when you're deforming, you know that QLZ is well behaved, like in the region. But are you assuming that the TS of Z is also well behaved and there is no kind of branch cut or anything?
Yes.
But I think it proved. I think because JLD domain may not extend to all region of Z plane where the analytic domain exists.
Actually, yes, I know, because I think it is not proved really, but I think people assume that it is. So first of all, I've assumed that there is no pole in between. So Z naught on the right hand side is corresponding to threshold, like 3-channel threshold.
Right.
So in the Z plane, they assume that there is nothing in between and it is analytic. But you are true. Strictly speaking, there are specific different kind of analytic domains have been proved. But
so you are basically in a sense assuming this extended analyticity.
Yeah, right. I'm assuming that this is there. And in fact, when I'm finally blowing the arc to the infinity, that is also assuming that in the complex Z plane, in this blowing the arc to the infinity also do not have any in doing so it does not cross any singularity. Now, of course, so this cigar-like contours wrapping these branch cuts will actually give rise to TSZ, but then they will really give rise to a discontinuity with respect to Z, because because when you go that way you will get a discontinuity across the branch cut, and similarly for the right and left hand side. So properly speaking, if I just write it, now z is a function of t, and this side will give me a discontinuity with respect to t, the right hand side. So this will contribute an st, and this will contribute tust. Of course, in evaluating and discontinuity with respect to u, you have to express st and all this stuff in terms of u. So when I collect these things, everything. So this is number one. Number two is, of course, now what about this arc at infinity? I mean, what will be the contribution from the arc at infinity? Now the arc at infinity, whatever the contribution from the arc at infinity is controlled by two factors. So number one is that
before you move on, can you summarize what you are doing for past few minutes?
Okay. So what I'm trying to do is I'm trying to obtain an expression for example, this FLS that I originally wrote in terms of this PL Legendre polynomial. I'm now trying to trying to give another expression in terms of a new function QLZ, but such that now I will be doing the final integral in a complex Z plane, but across the threshold kind of stuff. Because this will later come in handy when we will do actually the large scale expansion of this FLS coefficients. So that is my final first goal that I need to do.
Sorry, Parthiv. Like, can you repeat, like, what is the difference between the top line that you wrote and the bottom line? What changed when you went from P to Q?
Oh, when I changed, okay. When I went from PL to QL, I introduced this relationship between PL and QL. This one, right. You can see this one. And so for example, suppose in this expression, sorry, if I just incorporate, so PN looks like PN is basically PN can be interpreted now as the discontinuity of QN across this -1 + 1. Right. So when I do that, when I incorporate that, I can write it as a contour integral wrapping this -1 + 1. Of course, remember. So what does it mean? So when you break this contour, how do you break this contour? So you take the QL value on this. It's a very small. It's very slightly contour. So suppose it's just this is epsilon. This is epsilon. Mm-hmm. So over this upper straight line, there's a QL Z plus I epsilon. In the lower straight line, you have QL Z minus I epsilon. Small semicircular contours, I mean, they can be made arbitrarily small, and so that contribution can be neglected. Okay. So finally, I've just written in this special form.
I see. Okay. Yeah. Thanks.
Yeah. So this is, for example, a similar kind of stuff is also done, for example, in Karen-Hua's formula of inversion formula, famous. In fact, just to make a comment, just to make connection with the recent stuff in conformal bootstrap, Karen-Hua's inversion formula is precisely the way he presents is precisely a Frossard-Weber formula in the case of conformal field theory. Of course, the only challenge in the case of conformal field theory is that these analogs of QL functions are not easy to obtain. I mean, they are. I mean, that was where the smartness of Karen-Hua's went. That he came up with these QLZ functions. Okay, so this now the important point is this contribution from arcs at infinity. They are controlled by two. First of all, QLZ as mod z goes to infinity behaves as z to the power minus L minus 1. This is actually quite evident from the expression in terms of 2f1 that I wrote. So if I just look at there is a dz, there's a QLZ, and there is, for example, TTSZ. So this one now goes as z to the minus L minus 1. So here we will need to use that Regge boundedness kind of stuff, Regge boundedness kind of condition, and here we it's only the edge boundary is in the T channel. So really, this goes like z to the power j naught. So this goes like mod z to the power j naught. This is also mod z to the power. So this whole infinity. So this becomes now.
So Parthiv, what are the properties that dictate the follow behavior of QL or the function?
Oh, okay. Just let me show this. So QL, remember the definition of QL. So I mean, it can be shown from seen directly from here. So Q new had this expression. So it was some new dependent factor, but it was essentially this z to the power minus nu minus 1 is sitting there, and the 2f1 is in terms of 1 minus z square. So 1 minus z. So this is a series in infinite series in powers of 1 minus z square. So the leading term will go like z to the power minus nu minus 1. So if you send mod z to the power infinity. So basically it's a follow.
Okay, thanks.
Yeah.
Oh, sorry, that was 1 minus z square, is it? I thought 1 by z
Yeah. 1 minus z square.
I see.
1 minus. I mean 1 by z square. Like. So
Okay.
it's
yeah. Thanks.
Okay. So yeah. So that means this infinite. So for L greater than z naught, this contribution is actually vanishing. I mean, it's not really one greater, but it also has with the it's like one because otherwise it will be a logarithmic kind of stuff. So for L greater than z naught plus 1, this will be a vanishing. I mean, this contribution can be actually dropped off. Thus, for L less than z naught, this contribution is not this contribution from infinity arc will be actually something to think about.
I think this J naught would be also function of S as you explained earlier.
Yes.
So you have to assume that it can be only for certain region of S you can apply this thing that L greater than.
Yeah, but I think right. But I think of course when it's a function of S, but I think in the original derivation they always assume that J naught is greater than 2 or greater than equal to 2. So that this formula, so whatever the S is, that like ultimately J naught is J naught is like proxy of spin. So I mean, you of course express in terms of an S, but yeah, ultimately I think they assume it for.
Yeah, I have not understood one point that you are talking about.
Yeah.
So you are talking about spin many times, but you are scattering the scalars, and L is just in a sense some legendary polynomial L, whichever is there.
I mean,
it is spin?
No, I mean actually, in the literature, people call that L to be the spin. I mean, it's not the spin. So, for example, it's not the spin in the usual sense we call. I mean, in the usual sense we mean the particle. So, I think the way one should understand is that as if this. I mean, it's a confusing notation, but if you actually go through this derivation, they will always say that this is spin kind of stuff. But I do not know. Yeah, why?
Parthiv, your voice actually broke a lot during your last answer.
But yeah, it's spin. Yeah. Oh, okay. So now is it audible clearly?
Seems better.
Yeah. So all I am saying is that I do not really know that why do they call this spin, but I have seen this like standard books where they call like Gribov's lecture and so on. So they call this
Sorry, Parthiv, I think your voice is breaking again at the same place actually.
Just take
Parthiv, you're not very audible.
Just consider this like L.
Go ahead.
Yeah. Okay. So yeah, I was just saying that. I really do not know why they call it spin, but it's really, as you said, the L is that quantum number that enters the um, the partial wave expansion. So yes, so yeah, right. I don't know exactly why they call it spin, but yeah, but they call it spin in the standard literature kind of stuff.
Yeah, means is it the fact that since you have expanded all these things P1 plus P2 equal to 0 condition on the S2 in the configuration space, and they are the symmetry group is SO3, so can one think this expansion L is some kind of representation of SO3 group? That's why L is kind of a SO3 spin with integer value.
Yeah. I think yeah. Then I think that that is the right thing to think about. Yes. Yeah, right. Yeah.
Hi, Parthiv.
Yeah.
So when you wrote this earlier, this J0 was a function of t, right? Now it
No, that I wrote in the that I wrote in the S channel. So just to just to.
So is this the same function where you just replace the argument, or like you mean?
Yes, I mean that has to follow from the crossing symmetry.
Oh, okay.
Yeah.
Okay.
Okay. That is the case. So let me write down the final formula. So the final expression is
Parthiv, which slide are you on now?
Yeah, for slide 43.
Okay.
Okay, so the final expression is this one. So finally we have to so we have two pieces of integrals actually now currently. So if we can now drop this infinity arc at infinity, we have FLS as 16 pi square z naught infinity dz QL z tt s. Just writing this way. You can always now further we can use that QLZ is equal to minus 1 to the power L QL of minus Z. That property is already there, and also TU of S of UZ equal to minus TT ST of minus Z. So yeah, you just this is just plain old algebra. I mean, following some algebraic structure, you can obtain this two representations, and using these two, you can finally write down. So I'm going to the slide 44. You can finally write down FLS 1 by 8 pi square S plus 4n square S minus 4n square infinity Z QZ TT S of Z, where of course now I'm writing this thing as so where at this point I have written it as a real L to emphasize the fact that now we can actually analytically continue in L. In this formula, FL is not necessarily valid just for integer L, but also for any kind of real L for which it is valid. So this is the final group of formula, and this formula will be actually central of our large spin expansion of this FLS that we'll do. But for even before going that, for the large spin expansion of FLS, we will need some more information about this discontinuity of this TT term. So this discontinuity of TT term, especially.
Hello, Parthiv.
Yes.
So why you are calling after this expression that you can analytically continue L to be complex values? Because QL is still defined, I think, for integer L's, or
no. QL can be defined for any L, because so for example, the expression that I wrote QL in terms of 2f1, that is valid for any L.
Okay.
So let me just go to flash this. So it is in slide number 36. So for example, what this news are basically L's. So
right.
this so news are L. So as you can see, this is like 2f1, and in the 2f1, these news you can take complex, I mean, at your will.
Okay.
So that's why I'm telling that, so this formula, this Frossard group of formula. So now I'm in slide number 43. This is also, sorry, not 43, 44. So this formula is also the starting point of the Rege theory. I mean, when you construct the Rege theory, your starting point is also this thing only. You do it some other kind of stuff more carefully. But we won't go into Rege theory. We will just our final goal is to do a large spin expansion. So large spin expansion meaning large L expansion. So for example, we will do an expansion of this FL in the limit of large L. Of course, then the question is that how that will be of course that will be an expansion in 1 by L, just like people do in the CFT Bootstrap. But then there will be a question that how much we can do for finite L. But there is a problem. Of course, you can understand that this formula is only valid for L greater than some J naught. So for example, L equal to 0, this formula is not valid, because for L equal to 0, you have to now take care of, you have to consider that you have to consider the infinity at arc. So really L equal to 0 is the ultimate, that will be the puzzling point that will come. But even before doing that large spin expansion, we will need some knowledge about this this discontinuity of TT. So yeah, so for that we will be needing to go into unitarity. But before going there, I would like to say that whether there is any question regarding so far.
Yeah, Parthiv. So regarding this asymptotic behavior, you can only obtain values or the behavior of AFL for large L, right?
Yeah, I mean, ultimately we will do it in the large L, but then we will try to see that to what extent we can bring it to the finite L or something like that.
I see.
Yeah, but it will be essentially the initial perturbation that we are going to do. That will essentially a series in 1 by L.
Mm-hmm. And regarding the connection between L and nu, I missed your comment actually. So
oh, okay. Okay, so the definition that I gave. Okay, let me just write down.
Yeah.
Just it was in. Yeah, it is in this slide number 36. So there I just wrote this nu as the so that nu is just the L. That is what I was just telling.
Okay. So you're basically replacing that same Q nu into that QL.
Yeah. Right. Yeah.
Yeah, Parthiv. So this formula is valid for identical particles, or the valid for
yes. Because I've it's identical. No, sorry, no. It's identical, not identical particle, because the starting point of this was the partial wave coefficient, so that partial wave expansion. partial wave expansion is valid for, I mean, I have written it for identical particles, but it is valid for any particles whatsoever. Only, for example, this 4m square will be very complicated functions of stuff. The only thing I've taken care is that everything is scalar. That's it.
Okay. Thanks.
Okay. Okay. So now our focus will be to understand this discontinuity of the TT and stuff, because that will be because what we really want to understand is this, that what is the region of this. I mean, when we'll do this large L kind of stuff, what will be the region of the integration of Z that will actually contribute? So that we have to find out. And for that, we will need to study this TT, or this discontinuity in the Z plane, or the Z behavior, or equivalently in the T plane. Okay, fine. Okay, just go to the next slide. Which slide I am on? Okay, so slide number 45. Okay, so for this we will need to use stuff from unitarity. So far we have not used any information of unitarity. We have just relied on only the information about the analytic structure. So unitarity is simply it's just S bar S equal to identity. Recall S was SIT, which ultimately gives this kind of expression. So this is, and this is the unitarity expression that we are going to use, of course. Now, if I proceed on both sides, of course, we will going to take 1 by I some P4, P1, P2. We are just taking this thing. But now we're going to insert on the right hand side a resolution in identity, resolution of identity in multiparticle states, all kinds of multiparticle states. Only this resolution of identity will be used in the asymptotic Fox, Fox states of that we have already done. So for doing so, just to mention what we are going to insert here is we are going to use infinity
So Parthiv, here while inserting this identity operator, do you need information of all the possible particles with spins and everything that can be exchanged?
No. We are actually this identity. So for example, this identity we are using, this identity meaning some kind of completeness relationship, but we are inserting this only for the asymptotic Fox states, like the in-out state that we are talking about. So in that state, we have only as stable particle, we have only the scalar particles, one scalar particle that is of mass m, and all other states are basically multiparticle state of that single particle. So it is that we will just using that. So it's not over kind of all possibles. It's not like in quantum field theory, whatever possible interacting stuff going on and so on. So it is just those in and out spaces in which we are going to introduce these particles states. So for example, this state, this P1 going to, this P1 going to P2n, what it really means that there are 2n particles. This is a 2n particle state, but it's a 2n particle state. We have just assumed that each of with mass m. So it's a 2n particle state, but all particles are actually same particles, which is just the this same spinless scalar particle.
Are
So
you assuming some kind of Z2 symmetry? Otherwise, you can also allow odd number of particles.
Yes, I'm actually assuming Z2 symmetry here. Actually. That there's only even number of spins. Sorry, even number of particles. Yeah. So that's what I was going to write down. That I'm assuming Z2 symmetry. So Z2 symmetry, so that only even number of particles are there. Even number of particles can be there. I mean, not even number of particles can be there. It's wrong. What we really mean is that the states, there can be only even number. So that means that if I look in this structure, so ordinarily there is a threshold at 4m square, 9m square, 16m square, and so on and so forth, and then so on and so forth. But now I do not have this 9m square threshold. Under this circumstance, I do not have this 9m square threshold. So I have just 4m square and 16m square. So 4m square is basically the threshold for 2 going to 2, and 16m square is beyond which there is a possibility of 2 going to 4 particles. So here it's like AA going to A plus A, but here it can be A going to A plus A plus A. 4 particles can be, it can be other kinds of particles can be produced also, if we allow for that kind of stuff. So now this region, so for example, this S 16m square and 4m square, this will be called basically what elastic unitary region, unitarity region, elastic unitarity region. So why it's called elastic unitarity? Because within this domain, whatever I'm just getting A plus. I mean, in this case, A plus A going to A plus A. There is no other particle. So that is what we are going to tell. So this will be called, well, this is not elastic unitarity. There is nothing unitarity is happening, but this is called an elastic region because we will have just the A going to A kind of stuff. Okay, I'm not going to do the algebra because now the subsequent algebra will be pretty lengthy. But if I am just within this elastic unitarity region, so I'm going to the slide number 47 now. So if I am just in this region, that means S is 16m square and 4m square. Then only this any so then on the right hand side I will only have P1 P2 and then T. Okay, this was like, so this is like P1 prime, P2 prime, P3 P4. So this, so the right hand side of the unitarity equation will look like that, look like this. Now, yeah.
Can I ask a question? Like,
yes,
so is that like allowing S to be below 16m square? Are you kind of thinking that in say 5/4 theory in perturbative setting only one loop diagram you are considering in a sense, beyond loop leaving all the other?
Yes, yeah, right, yeah.
So this is not in a sense like for non-perturbative setting, I think, like
no. Why it's not? See, in the part of in the no why it's not in the because it's just some energy range. There's nothing perturbative I'm going to talk. I mean, so in the perturbative sense, you for even in the one loop you put this. I mean, when you integrate, you're putting those particles to some off shellness you can allow. But here it's everything on shell states. But I think there can be a similar kind. Maybe I'm not very sure. So I really have not thought about this connection, frankly speaking. Okay, now to make sense of this. Okay, so okay. So if I will not go into the details of the algebra. It's a very long algebra. But if I just I mean I have to do this whole bunch of integrals to take care of this q1, q2, and so just to remember this. Just to recall this. Just to refresh memory, this dq1 dq2 is 1 by 2 factorial dq q1 dq q2 2 pi to the power 6 2e q1 2e q2, where eqi is actually equal to qi whole square plus m square. Yeah. So this is just to recall this. This was the integration measure. So if you do this integrals finally, you will reach an expression, and that is what really makes sense for us. I mean, if you see the algebra, I will put it in the notes that I'm going to upload. I mean, it's there in the notes actually. So yeah, so that algebra. It's also there in Zubotov's paper, really, in the recent paper. So okay. So this expression is looks like this way. Only this is in S channel, but so it's scattered because the left hand side of the unitarity equation. So if you go to, for example, the slide number 45, the left hand side will give the discontinuity of t with respect to S. If you are, I mean, when you are considering to be the S channel kind of stuff. So ultimately, the expression will look like this. Where t plus minus st is actually limit 0 plus epsilon t, and p4 expression for p4 is a little bit complicated, but p4 is 2 pi to the power half comma half half. Where the on the numerator, what is sitting is basically the Heaviside step function. So this is the expression. So this is what they call the elastic unitarity equation. So this equation they call the elastic unitarity equation. Okay. Any questions?
Yeah. So where are you getting this equation from? Meaning the P4 that you have written. Like, is there a way to derive this equation?
Yes, obviously. So I'm not going to the algebra. It's a little bit longish algebra. So I'm not going to the algebra there. So if you do this, when you do this, complete these integrals, you will be able to do it this kind of stuff.
Can I make an online statement how to get this P4? I think the thing is that like, because you have to integrate over this dq P1, dq Q1 and dq Q2, which you have inserted in between. And there, if you do the mod values of the Q1, Q2, you will live with the angular variables. If you now transform this angular variable in terms of this z prime, you will get this expression. This theta function in the numerator basically tells us that cos theta have to be less than equal to less than equal to cos theta prime plus cos theta double prime.
Yes.
So
Right.
that bounded gives the theta function.
Yes, exactly. Yeah. Okay. So right. Okay, but this expression is derived for, okay, let me just understand, let me just tell you this thing. So this expression is derived for s greater than, of course, s lying between 4m square and 16m square. But in writing t plus and t minus, we've taken the liberty that we are slightly off the real s axis by the complex thing. But this is also derived for t negative. But t negative for t, I mean t negative and t negative for physical t. So this thing is derived for. So let me just write down that this expression is derived for this expression is derived for s, of course, 4m square 16m square and t less than 0, but t is physical. That means cos theta equal to 1 plus 2t s by 4m square. This is 1. So keeping here, so with in this physical domain, that is defined. Maybe t is not the right name. Z. Now we would like to analytically continue. So now the next step is analytically how can we analytically continue this expression in t. So we will now keep the s fixed, but we'll try to do this analytic continuation in t. But there's a problem that in this expression I cannot analytically continue in t this expression directly, because here t enters through this z. It's just z, and this z is sitting in the argument of a step function. So that is an utterly singular function, a singular object. So I cannot really analytically continue this guy. So I have to go to some other representation. So in order to make sense of this analytic continuation. Now you must be wondering why we are doing this analytic continuation, because but what if, because why we do need to go to the off the t-axis, because from this physical to unphysical kind of t, because analytic continuation is really meaning I'm going to unphysical t, because this unphysical t will be this unphysical region, this expression which is valid for unphysical t will be required when we ultimately do the large sphere expansion. Okay. So for analytically continuing t, what we'll do is this. So we will take help of an contour integral kind of stuff, a similar kind of so the basic mathematics or the basic procedure that goes like was the same procedure that went into derivation of the FG formula before. So we will introduce a contour integral around the physical value of stuff, I mean, we'll introduce a contour integral and then we'll blow up the contour integral and deform it according to our will. So that is the basic logic. So to tackle to tackle this thing, I am going to focus on this T plus, and this T minus.
Parthiv, can you tell me which slide are you in now?
Yeah, slide 48.
48. Oh, okay.
Yeah. So I'm going to I'm really going to rewrite this T plus and T minus in a clever way. I mean, it's nothing clever. I'm just going to introduce a contour integral for T plus and T minus. And then first I will do those integrals. Sorry, so I will do introducing that. I will actually change some order of integrals. So let's see how we do this. Okay, I'm going to slide 50. Okay, so the first thing is you introduce note that even so if I go to slide number 48, here this z prime and z double prime, they are also integrated in -1 to in the range -1 to +1. So all I'm using, I'm using a contour integral representation of, I'm using the simple Cauchy integral, and of course I have, I mean, of course we are in some analyticity domain, so we are assuming that within that -1 to +1, and I'm taking such a contour that over there this T plus and T minus are analytic. Then I can write down this T plus T minus just as in this slide 50. This T plus minus as a Cauchy count, as a Cauchy count kind of integrals using this Cauchy integral formula in this form. So next I'm going to incorporate this integral representations into that expression of elastic unitarity, so that I will be left with an expression of this kind: Ts ST, which is I'm just writing as a set. I'm just dropping the proportionality factors. Times T plus S prime, T minus S prime. This is also an integral. What there? K4 where K4 by definition is this one. So this is the, for example, the expression for K4 that we obtain. So that's, so now my elastic unitarity relation is this one. Just to highlight, it is this one. So now I have this T plus T minus and K4. Now interestingly, this K4 is an integral over P over P4, and that is what we will give an analytic expression. So let me just write down the explicit form of the K4, which is, you can do it very simply using the form of P4. So K4 turns out to be If you do this integral, K4 turns out to be so 4 pi by 3 by 2 of eta plus infinity eta by z 1 minus eta plus half minus eta minus half. So where eta plus minus is eta double prime square whole square. So this is for eta double prime, but then 1. One can write this integrals in this in this fashion. Okay, so here what you have in writing this thing, we have again used that explicit form of the P4 to go this kind of structure, and here now the Z I can actually analytically continue in Z because Z is really sitting not in a Z is not really not sitting inside any kind of wrong functions or problematic functions like step function or something like that, but rather it is sitting in a this kind of stuff. So this is this guy is known as Mandelstam kernel, using which you can analytically continue. So strictly speaking, my analytically continued elastic unitarity equation is this one. Okay, any questions? Though it's very technical, fairly technical question steps, but yeah. Any questions?
Yeah, so just can you summarize in say 30 seconds from the T how you got this K4?
Oh, from the T.
I mean from the T plus minus.
Oh, okay. So in the T plus minus, in the T plus minus, I wrote this T plus minus in this form of contour integral, and then I replaced that contour integrals in the original expression.
Okay.
And then I changed the order of integration. And changing that order of integration, so there was P4, there was okay. Let me just go to this the slide number 48. So here at the outside there was just dz prime and dz double c double prime integration, and t plus t minus, and for t plus t minus I replaced it by that contour integration, which was like this, like that I wrote in slide number 50, first line, and then I am bringing this contour integral on the right hand on the outside, and I'm doing first this z prime and z double prime integrations, and when I do that integration of T4, that's how I'm getting this K4. So what I'm really left with, so you see this in this expression for TS, I'm still left with two contour integrals, eta prime and eta double prime. Yeah, so that's how I traded that. So I basically traded that that badly behaved function for two contour integrals, which I'm going to deform.
So the K4, is it badly behaved function that you have separated?
No, not K4. It was P4, because P4 we had a step function, right? Yeah, P4. So we went from, because P4 was a step function and the variable that we wanted to analytically continue was really Z, and Z was sitting inside the step function. So we wanted to go to some other function where this is not the case. That's why we went to this K4. So now it is in this form. So in this expression, even though it's so in anywhere here we have not gone beyond -1 to +1, but now in this final form, I can analytically continue Z away from the physical value that's -1 +1. Now I can in complex Z plan. So yeah, this is the K S. Okay. Yeah. Okay. So we can massage this. However, there's a problem, and this problem is that usually, you know, even in conformal bootstrap, in doing the large spin expansion, what is very crucial thing that goes into this large spin expansion stuff is actually goes crossing, because crossing is the point by which you relate this large spin expansion to some another expansion. So here the only problem is that this discontinuity of T is not crossing symmetric, because you know you have just taken a very asymmetrically one discontinuity with respect to just S channel. So that cannot be this guy TS cannot be a crossing symmetric object. So we will need, so for doing actual some large spin expansion kind of stuff, we will actually need some crossing symmetric quantity. So that crossing symmetric quantity is what is known as, so I'm up to now slide number 52. So double spectral density. Spectral density, which is nothing but, so rho ST is equal to imaginary of T TST. So let me just understand what is imaginary of S, just to imaginary of S of TST was limit by Ti. Now imaginary of T, imaginary of S, TST is, you know, you do another, you take another discontinuity, but now with respect to T. So finally this expression comes out to be like this. This. So this is what this expression for. So this is what this definition of this rho ST. Now it's very straightforward to see from here that rho ST is indeed crossing symmetry. Rho ST is indeed crossing symmetry. So after the amplitude itself, TST equal to crossing symmetric. Now we have another object, which is the double spectral density, which is also crossing symmetric. So what we will do, we will try to obtain that elastic, so the elastic unitarity equation for this double spectral density, function, because it is that expression that will ultimately lead us, help us to the ultimately it will lead us to the large spin expansion. So let me just, I'm almost time up, but let me just start this stuff. So
Parthiv,
if we
you
look
can
at,
take 5-6 minutes extra since you lost some time.
Okay. So we will start from this expression, this final expression in terms of this K4. K4. I mean, so let me just once again write down. So I'm in slide number 53. So I had TSST equal to S minus 4m square S 1 by 8 4 pi square by I t plus S dot prime S prime times K4 eta prime eta double prime. And now I take the discontinuity with respect to t on both sides. So for example, the only place that is on the right hand side, the only place that is going to enter is in taking this discontinuity of K4, because K4 is a function of Z, but Z is a function of T. So K4, taking this imaginary part of this K4 with respect to T. So now we have S 8 into 4 pi square two pi I t plus this inverse t minus is double prime times imaginary of t K4. So it is this equation that is the starting point of our this. So I want to stop here because after this it will be fairly technical, so it will take some time. Yeah. So it will be this equation from where we will start our next lecture's stuff, because it is this equation, we will massage this equation into a form that will ultimately be our key object for having the large spin expansion of the FLS that we are aiming for. So that is the ultimate goal. Yeah, I'm going to stop here. So any questions?
Yeah. So okay, first let us thank Parthiv for this wonderful lecture. If there are any questions, please go ahead.
Yeah, so I was a bit lost towards the end. So why do you require this double discontinuity?
Okay, so I mean, of course, this double from our perspective, like what we want to do, we would like for this large spin expansion, we will need this double discontinuity to work. I mean, most importantly, double discontinuity is a crossing symmetric. So we wanted to have a elastic unitarity equation or something like that, which is which involves some kind of crossing symmetric object. So that is why we will need it. So in fact, when we will do this large spin expansion, I will show you. So I will show you explicitly that why it's always done with respect to this rho st. That is what that will enter there.
You see, what I mean is that if you don't go to this large spin expansion, within the things that you have done so far, meaning Mandelson kernel, after that, do you anywhere require this double discontinuity thing?
No, I think double discontinuity is interesting because so okay, first of all, you see this double discontinuity is so far what I've been talking about. I mean, even the kind of expressions. I mean, this double discontinuity was first introduced in Mandelstam when we tried to write down this what he called a double dispersion relationship. So recall last lecture I wrote down a dispersion relationship, but it was in a single variable. But Mandelstam wrote a full-blown. Mandelstam wanted to write a full-blown dispersion relationship, and that is where he introduced these double spectral densities. So I think that is why. a lot of study has been done on the analytic properties of this double discontinuity discontinuity function. But for our purpose, I will be just, I mean, the way I want to connect it to through this large spin expansion. But this, so apparently this, so for example, this positivity of rho st has this important as a consequence this this so-called Axe theorem, which tells that there has to be particle production and so on and so forth. So yeah, I think that's why. So that's a separate kind of line of stuff. I think people wanted to prove this Mandelstam dispersion relation sheet. So yeah, they wanted to investigate. For our purpose, like just the large spin expansion of effect.
Okay, so hopefully in the next lecture we will see the utility of this.
Yes. In the next lecture we will see this large spin expansion, and that then there we'll see this why this double discontinuity is important.
Parthiv, I have a physical question, I think, which I already asked you before. So, like in the region when S is 4m squared to 16m squared, right? So you are using the elastic unitarity relation, where basically you are allowing only two intermediate particles to exchange.
Yes,
right. So like say in 5-4 theory kind of process, should we really expect that this only is possible when there is a one loop diagram with 2, 4, 5 vertices, and by unitarity cuts using cutting rule you will only get 2 point, and higher loop diagram would not contribute to such kind of things?
Yes, I would say that I think participatively that the cutting way, I think that is how you want to think, something like that. Maybe if you cut that one loop diagram, because higher loop diagrams you can have this multiple particle kind of stuff.
Because the question when I'm asking, because then the utility of the whole these things, right, that we can determine all these non-participatively many things.
No, but the point is that, so for example, even in doing this elastic unitarity, so one of the things, so let me just come very cleanly. So I'm really following this, this recent work by Zibarda. But what I feel is that this elastic unitarity leads you in a controllable fashion to, even for a large spin expansion, only the leading terms. So for example, the subleading terms, you have to take consideration of this multi-particle cuts, and that is how that will be important. So if you want to have the subleading correction, and that will be important to understand. Ultimately it is still not understood, of course, and we are trying to understand, and from our point of view, that how we can understand this multi-particle cuts to take care, because multi-particle cuts, how to do the systematic. So for example, if you want to have a systematic 1/L expansion, one need to go beyond these 2 particle cuts.
Okay, and also like if you go to suppose in the intermediate channel, if you allow suppose 4 particle exchange, then obviously the amplitude like TT dagger, that will become now a 2 going to 4 amplitude and a 4 going to 2 amplitude. Roughly, right? And you cannot use probably only ST as the variables, because now you have a 6-point amplitude and you have a many scattering angle, in a sense, like you don't have only one jet but probably Z1, Z2.
Yes.
Things,
Right. Yes.
And I think can one have a for this the kernel whatever you define?
Yes.
K4 analogous thing exists in literature. Is there existing another?
No, I mean, I do not know, but I think so I only followed it through Ziberdov's work and something, but I do not think it's not that developed. I think elastic unitarity all this elastic unitarity, at least for 4 dimension, what I'm doing is already been done. What Ziberdov really did is that in higher dimension, and only the new thing he did in recent work is basically this large spin expansion in a way which is much closer to the conformal bootstrap kind of stuff. But I do not know that whether similar exploration has been done, as you said, when there's multiple particles going on in intermediate, like Mandelstam. What will be the analog of this Mandelstam kernel kind of stuff?
Okay, thank you.
So is it right to think that multi-particle exchanges, meaning when you were introducing this identity to operator with multiple particles, does it anyway correspond to higher loop expansion?
Well, I would.
The perturbative expansion,
I would say
going to higher loop, because if you exchange 2 particles, then probably it means that you are still at 1 loop. I mean, I don't know if this is the right way to think, but I'm just asking.
Yeah, I think yeah. I mean, if you want to make that kind of connection, like for example, you are right, because if you so what does it really mean? So you're taking these are on-shell states, but if you cut a one loop, for example, in 5.4, if you cut a one loop, you basically, when you are cutting, you're basically introducing on-shellness into the structure. So you have now made two particles to be on-shell structures, and that you are right. And if you go to higher loop and you cut a higher loop amplitude from in between, you will get like more than two particles going to on-shell. So yeah, I think that way you can think of. Yes.
So your statement about this large spin dominance coming from say multi-particle or some finite number of particle exchange. So does it mean that like the one loop that corresponds to the largest spin exchange, and the
yes, I would say the largest spin, I would say that so like one loop will correspond to so for example, all of these are really abstract, but yes, we also wondered that why A did not test it for example, perturbative 5.4. So I would say that this leading term in the 1 by j I mean, the large spin expansion, that should come from like one loop kind of stuff. Yeah, I would say like that. In fact.
Okay, I think we can stop the recording now for today. So let's thank Parthiv again for his lecture.